Part 1. The question that has no edge. There is a question that has been living quietly at the back of human minds for as long as we have been able to look up at the night sky and wonder. It does not announce itself with drama. It tends to arrive in the small hours, when the world goes quiet and there is nothing left to distract you from it. You are lying there in the dark and your mind drifts outward, following the stars, following the faint smudge of the Milky Way arching overhead, following your imagination past everything you have ever heard about the size of space, past every number you have ever read, past every photograph from every telescope ever pointed at the sky, and at some point the question just arrives, quiet and enormous and impossible to look away from. Does it ever stop? When you go far enough past every galaxy and every void and every filament of the cosmic web, past the farthest thing any telescope has ever detected, past the edge of everything we can in principle observe, what is actually out there? Not what specific things are out there, not what forces are at work, or whether there are other civilizations, or what the temperature is in the deep dark between galaxy clusters, but the foundational, almost childlike question underneath all of that. Does space go on forever? Is there an edge somewhere, some final boundary, some place where the universe simply stops? And if there is an edge, what is on the other side of it? Nothing? But if nothing is out there, what does nothing mean? Can nothing have a boundary? Can something end without there being something on the other side of the ending? And if there is no edge, if space simply continues in every direction, without ever stopping, without ever repeating, without ever running out of new distance to cross, what does that actually mean? Not as a figure of speech, not as a pleasant way of gesturing at the majesty of the cosmos. What does it really, precisely mean for something to have no end? Because infinity is not a very large number. It is not the largest number. It is not a number at all in the ordinary sense. It is a completely different category of thing, and when you try to hold it in your mind honestly, rather than just skating over the surface of the word, something starts to give. This is one of the oldest questions in the history of human thought. Aristotle argued more than 2,000 years ago that the universe must be spatially finite, because if it were not, he reasoned, the stars could not complete a full rotation around the Earth in 24 hours. The argument was wrong in its physics, since the Earth rotates and the stars do not, but the instinct behind it was sound. Infinity creates problems that finite things do not. The philosopher Giordano Bruno argued in the 16th century, at great personal cost, that the universe was not only infinite, but filled with countless suns and countless worlds orbiting those suns. He was burned at the stake in Rome in the year 1600. The cosmological views were not the primary charge, but they were part of a pattern of thinking the Church found intolerable. The question of the universe's extent has never been merely academic. What makes it extraordinary in the modern era is not just its age or its drama. It is that science, with all of its extraordinary instruments and centuries of accumulated insight, has still not resolved it. Not because the question is in principle unanswerable, but because the universe is so large that the tools we have built, as extraordinary as they are, cannot yet see far enough around it to determine its shape. We are in the position of trying to determine whether the Earth is a sphere or a flat plane by examining a single square meter of ground. The local measurements are impeccably precise. The global inference remains uncertain. What we are going to do in this exploration is follow that question seriously and in depth, all the way from the basic physics of what we mean by the size of the universe, through the strange predictions of cosmology about what lies beyond our horizon, to the cutting edge of current research about the geometry of space, the physics of inflation, dark energy, and the ultimate fate of everything. We will visit the three possible shapes of space and what each one implies. We will explore cosmic inflation and why it predicts a universe that is vastly, possibly infinitely, larger than anything we can see. We will think carefully about what it would actually mean for physics and for human understanding if the universe turned out to have no boundary at all. We will also be honest about what we do not know and what we may never know. This is not a topic where you arrive at a clean final answer and go home satisfied. The honest conclusion is a carefully mapped territory of certainty, strong inference, and genuine open questions. But that honest uncertainty is not a weakness. It is what makes the subject worth following. The questions that resist easy answers are the ones that lead somewhere real. So let us begin with something concrete. With the universe, we can actually see. Right now, at this moment, the part of the universe that is, in principle, observable to us extends approximately 46.5 billion light-years in every direction from where you are sitting. That is the radius of what astronomers call the observable universe. The full diameter is roughly 93 billion light-years. Within that sphere, there are an estimated 2 trillion galaxies. Each of those galaxies contains somewhere between tens of billions and hundreds of billions of stars. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, depending on how you count the faint dwarf stars. Around many of those stars orbit planets. A light year is the distance light travels in 1 year, moving at 299,792 kilometers per second. 1 light year is approximately 9.46 trillion kilometers, 93 billion light years. The diameter of the observable universe is a number that requires 24 digits to write out, and that corresponds to nothing in any ordinary experience of scale. The observable universe is, by any human measure, unimaginably vast. And yet, it is not the universe. It is the part of the universe from which light has had time to reach us since the universe began 13.8 billion years ago. There is almost certainly far more beyond that horizon. How much more? That is exactly the question we are following today. And the answer, depending on which physical framework turns out to be right, ranges from enormous but finite to literally, mathematically infinite. The reason the observable universe has the radius it does is a consequence of 2 things: the speed of light and the expansion of space. Light travels at a fixed maximum speed. In 13.8 billion years, the maximum distance any light could have traveled to reach us would be 13.8 billion light-years, in a universe that was not expanding. But the universe has been expanding since the beginning, carrying distant galaxies farther away as the space between them stretched. The matter that emitted the cosmic microwave background was only about 42 million light-years away from us when that light was emitted, very shortly after the Big Bang. But during the 13.8 billion years that light has been traveling toward us, the expansion of space has carried the source of that light to a current distance of approximately 46 billion light-years. This is why the observable universe extends to 46 billion light-years in every direction, rather than just 13.8 billion. Beyond the edge of our observable sphere, there is no reason to think space ends. The universe did not emerge with a wall at the edge of what light could cross in 13.8 billion years. That boundary is a boundary of our knowledge and our observational reach, not a boundary of what exists. The actual universe, whatever its total extent, extends beyond our observable horizon, the way a continent extends beyond the horizon, visible from a ship in the middle of the ocean. The horizon is real. The continent beyond it is also real. We simply cannot see it from here. The question is, how far beyond, and whether that how far eventually ends, or whether it continues without limit. The difference between a universe that is merely very large and a universe that is genuinely infinite is not a difference of degree. It is a categorical difference. Distinguishing between them from where we stand is one of the deepest challenges in modern cosmology. If you are watching this right now and settling in for the journey, I want to ask you to drop a comment with where you are in the world and what time it is. The thought of people scattered across this planet, under different skies, maybe in different time zones, maybe some of you in full sunlight and some in darkness, all thinking about whether that darkness goes on forever, feels like the right spirit to carry into this conversation. And if you are new here, please subscribe. There is much more of this kind of exploration ahead, and you will want to be here for it. Now, let us talk about what infinity actually means when a physicist uses the word. In everyday speech, infinite is a hyperbole. You say someone has infinite patience. You describe a beautiful view as going on forever. These are emotional amplifications, not technical claims. In mathematics and physics, the word means something very specific. There is no largest member of the set in question, no final point in the space, no highest number in the sequence. For every value you can name, there is always one beyond it. In the context of the universe, infinite space means exactly this. There is no point beyond which there is no more space. You could travel in any direction for any length of time, and never arrive at a place where space ran out, not because you had not gone far enough, but because going far enough is a concept that has no meaning in a space without boundaries. The physical implications of this, if it is true, are extraordinary. If space is truly infinite and matter is distributed through it at finite average density, then the universe does not just contain a very large number of galaxies. It contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And because the number of physically distinguishable configurations of matter in any finite volume of space is finite, those configurations must eventually repeat in an infinite universe. Every arrangement of atoms that can exist does exist, somewhere in infinite space, and not just once, infinitely many times. This means, concretely, that in an infinite universe there is a location, unimaginably far away, but real, where a galaxy exists identical to the Milky Way in every measurable respect, where a star identical to the Sun shines at the center of a solar system identical to ours, where a planet identical to Earth orbits that star, where someone identical to you in every quantum mechanical detail is at this moment watching this exact video. The physicist, Max Tegmark, has estimated the distance to the nearest such copy of you at approximately 10 to the power of 10 to the power of 28 meters away, a number so vast it has no human name and cannot be traversed in any finite time. But in a genuinely infinite universe, that copy exists. Whether this is comforting, disturbing, or simply bewildering probably depends on temperament. But it is the honest mathematical consequence of combining infinite space with finite local possibilities. And it illustrates why the question of whether the universe is infinite is not an abstract curiosity. It is a question about the fundamental nature of reality and about what, if anything, makes any individual moment unique. Part 2. What infinite actually means in physics. The mathematician Georg Cantor, who in the 19th century, more than anyone else, developed the rigorous mathematics of infinite sets, spent decades working through the implications and reportedly suffered repeated mental breakdowns in the process. Whether the connection was causal is debated, but the story captures something real about the psychological weight of the concept when you try to hold it without the softening of metaphor. One of Cantor's most striking results is this: there are infinities of different sizes, and the differences are provably, rigorously real. The set of all integers is infinite. The set of all real numbers, all the decimals, is also infinite. But the second infinity is strictly larger than the first. You can never make a one-to-one pairing between integers and real numbers. No matter how cleverly you try, some real numbers will always be left without an integer partner. The real numbers form what mathematicians call a larger cardinality of infinity than the integers. Infinity is not a single thing. It is a tower of ever larger infinities, each one genuinely bigger than the one below. In physics, the word infinite is treated with deep suspicion. When a calculation produces an infinite result, that is almost always a sign that something has gone wrong, that the theory is being pushed beyond its range of validity, or that some physical process has been neglected that would regulate the result. The singularity at the center of a black hole, where general relativity predicts infinite density and infinite spacetime curvature, is not believed to be a physically real infinity. It is a sign that general relativity is inadequate at the Planck scale, that quantum gravitational effects must become important and would replace the singularity with something finite and calculable if we had the right theory. The Big Bang singularity is the same kind of signal. Extrapolating the expansion of the universe backward in time, using general relativity, you arrive at a moment of infinite density and infinite temperature and zero spatial volume. Most physicists believe this is not a physical description of the actual origin of the universe. It is a mathematical breakdown, a point where the theory stops having physical content because it is not complete at those extreme conditions. What actually happened at and before the Planck time, approximately 5.4 times 10 to the negative 44 seconds after the conventional Big Bang, is genuinely unknown. Yet physics may nonetheless produce a physically infinite spatial universe, not as a breakdown of a calculation, but as a statement about the initial conditions of reality. A spatially infinite universe would be a factual statement about how much space there is, not an artifact of a theory being pushed too far. These are fundamentally different kinds of infinity. The spatial extent of the universe is not determined by any equation within the standard cosmological model. It is an initial condition. The Friedmann equations, which govern the expansion, take as inputs the total amount of matter and energy, and produce as outputs the expansion rate and the curvature of space as functions of time. They do not output the total size of the space. The size must be specified independently, as a boundary condition, and the equations describe how distances within that space change over time. This is why the question of the universe's size cannot be resolved by calculation alone. It requires observation, and specifically, it requires observation that can probe the global geometry of space rather than just the local physics. What observations have told us, after decades of increasingly precise measurement, is that the universe's geometry is extraordinarily flat, to within a fraction of a percent of the perfect flatness that corresponds to infinite spatial extent in the simplest models. Everything points in the direction of a universe that is either infinite or so enormous that the practical difference is undetectable from inside our observable bubble. Consider what a flat universe actually means geometrically. In perfectly flat space, the rules of Euclidean geometry hold exactly. Parallel lines remain parallel forever. The angles of any triangle sum to exactly 180 degrees. The circumference of a circle is exactly 2 times pi times its radius. These rules hold everywhere, at all scales, with absolute precision. In positively curved space, those rules break down. Parallel lines converge. Triangle angles sum to more than 180 degrees. A positively curved universe is finite, with no boundary, looping back on itself the way the surface of a sphere does. In negatively curved space, parallel lines diverge. Triangle angles sum to less than 180 degrees, and the universe extends forever. 3 geometries: flat, meaning infinite in the simplest topology; positive, meaning finite and closed; negative, meaning infinite and open. The curvature is determined by the total energy density relative to a specific critical value. If the actual density equals the critical density, flat; if higher, positive and finite; if lower, negative and infinite. The critical density works out to approximately 9.47 times 10 to the negative 27 kilograms per cubic meter, roughly the mass of 5 hydrogen atoms spread over every cubic meter of space. The universe's measured total density, summing ordinary matter, and dark energy, is within about 2 parts in 1,000 of this critical value. The universe appears flat, and flat space, in the simplest models, is infinite space. This does not prove the universe is infinite. It proves the universe is flat within our observable patch. A positively curved universe with a radius of curvature 400 times larger than our observable bubble would look exactly as flat as an infinite universe to any measurement we can currently make. The curvature would be too gentle to detect from our position, but the evidence does point, clearly and consistently, towards something that is either genuinely infinite or so large that the word infinite becomes the only honest description. Part 3. The observable universe versus the actual universe. One of the most important and most commonly confused distinctions in cosmology is the difference between the observable universe and the actual universe. They are not the same thing. They are not even close to the same scale, and conflating them leads directly to a misunderstanding of the central question. When we say the universe is 93 billion light-years across, we are not describing the universe. We are describing the part we can see. The observable universe is the sphere centered on your current location, from which light has had time to reach you since the universe began 13.8 billion years ago. It is a sphere not because the universe is spherical, but because the speed of light, combined with the finite age of the universe, limits observations equally in every direction. An observer anywhere else in the universe has their own observable sphere of the same radius, centered on them, overlapping with ours, but extending beyond our horizon in directions we cannot see. Beyond the edge of our observable sphere, space almost certainly continues. The universe was not created with a boundary at exactly the radius of our light horizon. That would be a remarkable and entirely unexplained coincidence, a fine-tuning of cosmic geometry to match the observational reach of creatures on one particular planet in one particular epoch of cosmic history. There is no physical mechanism that would produce such a coincidence. Far more natural is that the universe extends well beyond what we can see, with more galaxies, more dark matter, more structure following the same laws, going about its business with complete indifference to whether we can see it. The specific reason the observable universe has a radius of 46.5 billion light-years, rather than simply 13.8 billion light-years, is the expansion of space. Light travels at 299,792 kilometers per second, over 13.8 billion years. At that speed, light can travel 13.8 billion light-years if space were not expanding. But space has been expanding throughout the entire history of the universe. While the light emitted by distant galaxies was traveling toward us, the space it was traveling through was stretching. The galaxies it came from were being carried farther away by that stretching, even as their light was heading toward us. The result is that light we are receiving today was emitted by objects that were much closer to us when they emitted it than they are now. The cosmic microwave background illustrates this perfectly. The matter that emitted the CMB photons we observe today was, at the moment of emission 380,000 years after the Big Bang, approximately 42 million light-years from our location. That light has been traveling through expanding space for 13.8 billion years. During that journey, the expansion has stretched the space between us and the source by a factor of roughly 1,100, meaning the matter that emitted those photons is now approximately 46 billion light-years from us. The light traveled 13.8 billion light-years. The source is now 46 billion light-years away. Both things are true simultaneously because of the expansion. The observable universe, containing 2 trillion galaxies and spanning 93 billion light-years, is already far beyond what any human intuition can absorb. But it may be a vanishingly small fraction of the actual universe, depending on the physics of the early cosmos. The key relationship here is between the observable universe and the total universe after inflation. Inflation, the period of extraordinary exponential expansion in the earliest moments of the Big Bang, stretched whatever volume existed before inflation by an enormous factor. The minimum required expansion factor for inflation to solve the problems it was designed to solve is approximately 10 to the power of 26. This means the total universe, after inflation, is at least 10 to the 26 times larger in linear scale than the observable portion, and therefore at least 10 to the 78 times larger in volume. A factor of 10 to the 78 means the observable universe is to the total universe as a single subatomic particle is to the observable universe, and then some. The human mind has no intuitive grip on such ratios. But the important point is this: if inflation happened, and the evidence that it did is substantial, then the universe we can observe is a tiny, tiny patch of the whole. And if inflation was eternal, if quantum mechanical effects in the inflationary field caused inflation to continue indefinitely in some regions, even as it ended in others, then the total volume of the universe is not just very large. It is literally infinite, growing without bound, generating new regions of space without end. The relationship between the observable universe and the actual universe is therefore a relationship between what the laws of physics allow us to know and what exists. It is not a relationship between a large thing and a slightly larger container. It is a relationship between a tiny local bubble of knowable reality and something that may have no limit at all. The universe is larger than our knowledge of it, probably vastly larger, possibly infinitely larger. The observable universe is our home, the portion of reality we can know directly. But it may be to the actual universe what a single room is to an infinite city. We know the room very well. We have almost no idea of the extent of the city outside. Part 4. How the Big Bang created space itself. The most widespread misconception about the Big Bang is that it was an explosion, a detonation in the middle of a pre-existing void, a fireball expanding outward through empty space, with matter and energy racing away from a central point. In this picture, if you could somehow travel back to the beginning and observe the Big Bang from outside, you would see a bright explosion in the middle of a dark, pre-existing emptiness, with debris flying outward in all directions. The universe would have a center, and if you traveled far enough in the right direction, you could find it. None of this is right. The Big Bang was not an explosion in space. It was the expansion of space itself, not matter exploding through a pre-existing void. The space itself, expanding, stretching, growing, carrying matter along with it as it went. There was no pre-existing void for the Big Bang to happen in. Space itself, at least in the form we know it, began to exist with the Big Bang, or at least emerged from a prior quantum gravitational state as the Big Bang began. You cannot stand outside the Big Bang and watch it. You are inside it. Everything is inside it. The Big Bang is not a place or a moment in time that you can locate. It is a state that every point in the universe went through simultaneously. This is extraordinarily difficult to visualize because our intuition about space treats it as a fixed, passive container, a stage on which events happen. In everyday experience, things move through space. Space does not itself move or change. The Big Bang requires abandoning that intuition at the deepest level. The standard analogy is the surface of an inflating balloon. Draw dots on the rubber surface with a marker. Those dots are the galaxies. Now inflate the balloon. As the rubber stretches, every dot moves away from every other dot. The dots are not moving across the surface. The surface itself is expanding. Every dot sees every other dot moving away. No dot is the center of the expansion, because the expansion is a property of the surface, not a motion across it. The center of the balloon's inflation is inside the balloon, in the three-dimensional interior, not on the two-dimensional surface where the dots live. For any being living on that two-dimensional surface, the expansion has no center. Every direction you look, you see other dots moving away. There is no special location from which the expansion originates. This is exactly what cosmological observations show for the actual universe. Every galaxy is moving away from us, and the recession speed is proportional to distance, meaning the expansion is uniform and has no center within the universe. Now, the balloon analogy breaks down in a specific way that matters for our question. The surface of the balloon is finite. As you inflate it, the area increases, but it remains finite. If the universe were simply the three-dimensional version of the balloon's surface, it would also be finite. But there is no requirement that the universe be closed like a balloon's surface. The universe could be an infinite three-dimensional space that expands uniformly at every point. An infinite space, expanding, is still infinite at every moment. The expansion changes the distances within it, but not the fact of its infinite extent. The crucial implication is that the Big Bang did not create a finite ball of matter in a pre-existing empty space. It was either the expansion of a finite, closed space, or the uniform expansion of an already infinite space. Both possibilities are consistent with the equations of general relativity applied to cosmology. The Friedmann equations, which describe the expanding universe, do not specify the total spatial extent. They describe how the scale factor changes over time. You can apply them equally well to a finite closed universe and to an infinite flat one. The Big Bang was everywhere. Whatever the total extent of the universe, whether finite or infinite, the hot, dense state at the beginning pervaded all of it simultaneously. Every point in the universe was at the same extreme temperature and density in the earliest moments. Every point has been expanding and cooling since. Every point is equally the origin. When people ask where the Big Bang happened and expect a location, expecting to be told there is a central point in the sky from which the universe exploded, the answer is everywhere. It happened at your location. It happened at every galaxy's location. It happened at every point in the entire universe, simultaneously. This dissolves a common confusion. The Big Bang cannot be used to argue for a finite universe on the grounds that it happened at a specific point. It was not a point source. It was a state of the entire universe. And the total extent of the universe before, during, and after the Big Bang is a separate question from the physics of what happened during that state. Now, the moment at the very beginning of the Big Bang deserves careful treatment because it is often misrepresented. General relativity, run backward in time from the current expanding universe, predicts a singularity at the beginning, a point of infinite density, infinite temperature, and zero volume. This singularity is not a physical description of the actual beginning of the universe. It is a mathematical failure of the theory at extreme conditions. General relativity is a theory of smooth, classical space-time. It was not designed to handle quantum gravitational effects. At the extraordinary energies of the very earliest moments, quantum mechanics and gravity would both have been important simultaneously, requiring a theory of quantum gravity that we do not yet have. The singularity is a sign that we are pushing general relativity beyond its range of validity. What actually happened at the Planck time is genuinely unknown. Loop quantum gravity proposes a quantum bounce, suggesting the universe contracted from a previous state was compressed to a very high but finite density, and then began to re-expand. The Hartle-Hawking no-boundary proposal suggests that at very early times, the quantum description of the universe involves a geometry in which time and space become indistinguishable at the Planck scale, smoothly rounding off what would otherwise be a sharp beginning point. String theory offers its own alternatives. None of these is tested. The actual physics of the universe's origin remains genuinely unknown. But what is important for our question is this. All of these frameworks still describe an expanding universe that very shortly after whatever its quantum gravitational origins were, entered the hot, dense, rapidly expanding state that we call the Big Bang. And from that state, inflation stretched it to its current enormous size. Part 5. The geometry of space, flat, curved, or closed. The geometry of space is not a property you can see directly, the way you might see the color of a wall. Geometric curvature at the cosmic scale is detectable only through precise measurements of how angles, distances, and the relationships between them behave across large spans of the universe. It requires measuring what things look like and comparing to what different geometric theories predict they should look like. Here is the core concept. In perfectly flat space, the geometry obeys the rules formalized by Euclid more than 2,000 years ago. Parallel lines remain parallel forever. A triangle, any triangle, no matter how large, has angles that sum to exactly 180 degrees. The circumference of a circle is exactly 2 times pi times its radius. These relationships hold everywhere, at all scales, with absolute precision. Now, take those rules to a curved surface, stand on the surface of the Earth, and try to draw a triangle. Draw one side along the equator, from a point in Africa to a point in South America, following the great circle of the equator. Now draw the other 2 sides going straight north from each endpoint to the North Pole. You have a triangle. Measure its angles. The angle at each corner where the equatorial side meets the northward sides is 90 degrees, a right angle. Both northward sides also meet at the North Pole, and they also form a 90-degree angle there, because the 2 lines of longitude are perpendicular at the pole. Your triangle has 3 right angles. Its angles sum to 270 degrees, not 180. This is positive curvature. The geometry of a sphere violates Euclidean rules in a specific way. Triangles have angles that sum to more than 180 degrees. Parallel lines converge, and the surface is finite and unbounded. You can travel in a straight line and never fall off an edge. You will just eventually return to where you started. Negative curvature, the geometry of a saddle, violates Euclidean rules in the opposite direction. Parallel lines diverge, triangle angles sum to less than 180 degrees, and a negatively curved space extends forever. It does not curve back on itself. So, flat space is consistent with infinite extent. Positively curved space is finite. Negatively curved space is infinite. The curvature of the universe is determined by the total energy density of the universe relative to the critical density. If the actual density equals the critical density, space is flat. If higher, space curves positively, and the universe is finite. If lower, space curves negatively, and the universe is infinite. Cosmologists have measured this energy density with impressive precision. The cosmic microwave background is the most powerful single tool for this measurement. The CMB has tiny temperature fluctuations, about 1 part in 100,000, that encode information about acoustic oscillations of the hot plasma in the early universe. These oscillations created a characteristic angular scale in the CMB that depends sensitively on the geometry of space. In a flat universe, this characteristic scale subtends an angle of approximately 1 degree. In a positively curved universe, the same physical scale appears larger. In a negatively curved universe, it appears smaller. The Planck satellite provided the most precise CMB measurements ever made. Combining Planck's data with independent baryon acoustic oscillation measurements, the result is extraordinarily constraining. Omega total equals 0.9993, plus or minus 0.0019. The universe is flat to within about 2 parts in 1,000, one of the most significant measurements in the history of cosmology. But here is the subtlety. This measurement does not prove the universe is infinite. It proves the universe is flat within our observable patch. A universe that is positively curved, but with a radius of curvature 400 times larger than our observable universe, would also appear flat in this measurement. The curvature would be too gentle to detect at the scale of 93 billion light-years. So the measurement is consistent with infinite extent. It is also consistent with a very large finite extent. Distinguishing between the two requires measuring the curvature with precision 400 times better than current state-of-the-art, or finding some other observational signature of the universe's global topology. There is also a distinction within flat geometry between simply connected flat space, which is the infinite Euclidean case, and topologically compact flat space. A three-dimensional torus, formed by taking a cube and gluing opposite faces together, is flat in the sense that Euclidean geometry holds everywhere within it, but it is finite. If the universe were a torus of sufficient size, our measurements would see flat geometry within the observable patch, and yet the universe would loop back on itself at larger scales. The search for topological signatures, matchings in the CMB that would indicate we are seeing the same physical region of space from multiple directions, has been carried out extensively. No convincing topological matches have been found. This rules out compact topologies smaller than the CMB last scattering surface, but it leaves open compact topologies larger than our observable horizon. What the geometry measurements tell us, in careful summary, is this: the observable universe is extraordinarily flat. The universe is either geometrically infinite flat space, or a geometrically closed space, so large its curvature is undetectable, or a topologically compact but locally flat space, with topology scale beyond our observable horizon. The flatness measurement points most strongly toward infinite, or effectively infinite extent, but it does not eliminate the alternatives. The reason this flatness is there at all, and the reason it is so striking, comes from the physics of the inflationary epoch. Part 6. Inflation and the Horizon Problem. In the late 1970s, careful analysis of the standard hot Big Bang model revealed a series of puzzles that had no natural explanation within the model itself. The model was highly successful, but underlying its successes were initial conditions that seemed to be extraordinarily fine-tuned in ways that no one could explain. The most pressing puzzle was the horizon problem. The cosmic microwave background is extraordinarily uniform. Its temperature varies by less than 1 part in 100,000 across the entire sky. This uniformity holds in every direction, including between points on opposite sides of the sky, separated by a full 180 degrees. Consider what those two opposite points represent. The CMB was emitted about 380,000 years after the Big Bang. At that time, 2 points on opposite sides of the CMB sky were separated by approximately 90 million light-years, but the universe was only 380,000 years old. Light, traveling at maximum speed, could only have covered 380,000 light-years in that time. Those two regions were more than 200 times too far apart for any signal to have traveled between them. In the entire history of the universe, up to the moment of CMB emission, they had never been in causal contact. No information, no energy, no influence of any kind could have passed between them, and yet they have the same temperature to 1 part in 100,000. In normal physics, systems reach the same temperature through thermal equilibration. They exchange energy until they reach a common temperature. You can only have thermal equilibrium between regions that have been in causal contact. Two regions that have never been able to influence each other cannot have equilibrated. They could only have the same temperature if the initial conditions were fine-tuned to be uniform across causally disconnected regions. This is possible, but it is a fine-tuning that the standard Big Bang model cannot explain. It merely assumes it. The second major puzzle was the flatness problem. We know the universe's geometry today is flat to within 2 parts in 1,000, but in the hot Big Bang model, flatness is an unstable equilibrium. Any slight deviation from the critical density in the early universe is amplified enormously by subsequent expansion. For the current near-perfect flatness to exist, the energy density in the first second of the universe must have equaled the critical density to within roughly 1 part in 10 to the 15. At the Planck time, the required precision was roughly 1 part in 10 to the 60. The initial energy density had to be equal to the critical density to 60 decimal places. Not impossible, but extraordinarily and unexplainably fine-tuned. In 1980, American physicist Alan Guth proposed a solution to both problems simultaneously. He called it inflation. The key idea was that the very early universe, before the hot Big Bang phase, underwent a period of extremely rapid, exponential expansion driven by a quantum field called the inflaton. During this inflationary period, the universe expanded by at least a factor of 10 to the power of 26 inches linear scale, in a time of roughly 10 to the negative 35 seconds. The solution to the horizon problem is elegant. Before inflation, the universe was extraordinarily compact. Every region was within the causal horizon of every other region. There was ample time for thermal equilibration to establish the same temperature everywhere. Then, inflation stretched this small, uniform, thermalized region by a factor of at least 10 to the 26. Regions that had been in contact were carried far beyond each other's causal horizons. The different parts of the CMB that appear causally disconnected are not actually disconnected. They were in contact before inflation stretched them apart. They are thermalized remnants of a common initial region. The solution to the flatness problem is equally direct. Whatever the initial curvature of the pre-inflationary universe, inflation stretched it out so dramatically that any curvature was reduced to an undetectable level within the observable patch. The mechanism is exactly like inflating a balloon to the size of the observable universe. A balloon that was crumpled and curved before inflation would appear locally flat everywhere, after being stretched by a factor of 10 to the 26. Inflation drives omega to 1 to extraordinary precision by simply making the universe so large that any initial deviation is diluted past detectability. Inflation also makes a specific and quantitative prediction about the statistical properties of the CMB that had not been anticipated before inflation was proposed. The inflaton field was a quantum field, subject to quantum mechanical fluctuations. During inflation, these quantum fluctuations were stretched from subatomic scales to cosmological scales. When inflation ended and the hot Big Bang began, these stretched quantum fluctuations became density perturbations, tiny variations in the density of matter and energy, frozen into the fabric of space. The prediction is that these density perturbations should have a nearly scale-invariant power spectrum, with roughly the same amplitude of fluctuation at all length scales, with a slight tilt towards slightly more power at large scales. When Planck and other experiments measured the CMB power spectrum in detail, the result matched this prediction with extraordinary precision. The spectral index was measured to be approximately 0.965, exactly in the range that simple inflationary models predict. This successful prediction is the strongest piece of direct evidence that inflation actually occurred. The flatness, the horizon solution, and the matching of the CMB power spectrum all point to an inflationary epoch as the natural description of the very early universe. And here is where inflation connects to the size question in a way that is fundamental. Inflation stretched the universe by at least a factor of 10 to the 26, almost certainly by much more. The observable universe is a tiny region of the inflated cosmos. But what happened to inflation outside our observable region? When quantum mechanics is properly included in the physics of the inflaton field, the answer is striking. Inflation tends to go on forever, not in our region, but somewhere. The theory of eternal inflation and the multiverse it implies follows directly from the combination of inflation and quantum mechanics. That is where we go next. Part 7. Eternal inflation and the multiverse. Eternal inflation is not a separate theory invented for exotic purposes. It emerges naturally and almost inevitably when you take the basic physics of inflation and combine it properly with quantum mechanics. Its implications are profound. It makes the universe literally infinite, and it produces the possibility of a multiverse, an endless generative process creating new cosmic regions without beginning or end. Here is how eternal inflation arises. The inflationary epoch is driven by a quantum field called the inflaton. In the simplest models, the inflaton starts in a high-energy state and slowly rolls toward a lower-energy state as the universe expands. When it reaches the low-energy state, inflation ends. The energy stored in the field is rapidly converted into a hot bath of particles, and the hot Big Bang begins. In a classical world, this would be uniform. The field rolls at the same rate everywhere. Inflation ends simultaneously everywhere. But the inflaton field is a quantum field. It obeys quantum mechanics, which introduces irreducible randomness. The field does not roll at a perfectly uniform rate. It rolls on average, but with quantum fluctuations superimposed. In most regions, the average rolling wins out, and the field progresses toward the end of inflation. But in some regions, a quantum fluctuation kicks the field back up the energy slope, temporarily reversing its progress. In those regions, inflation continues. Here is the crucial asymmetry in the growth rates. Regions where inflation continues are expanding exponentially. Regions where inflation has ended are expanding more slowly at the rate of a hot Big Bang universe. Exponential growth always outpaces any slower growth. Even if only a small fraction of regions at any moment are experiencing quantum kicks that keep inflation going, those regions grow so rapidly that they always dominate the total volume. The inflating background never depletes. It keeps growing, keeps seeding new bubble universes, keeps generating new regions of space indefinitely. This is eternal inflation. Once inflation starts, it does not stop everywhere at once. It keeps going in some regions indefinitely, generating a perpetually expanding background of inflating space within which individual bubbles of non-inflating, hot Big Bang universe keep forming. Our observable universe is one of those bubbles. Beyond our horizon, perhaps the inflating background is still there, still generating new bubbles, still expanding. The total volume of space in the eternal inflation picture is infinite. The inflating background grows without bound. The total number of bubble universes produced is infinite. The total history of the cosmos produces infinitely many separate cosmic histories. The separation between bubble universes is permanent and absolute. The space between them is inflating faster than light can cross it. Two bubble universes that formed from the same inflating background cannot ever communicate, cannot exchange signals, cannot interact. They are cosmologically isolated for all time. Each one evolves independently, beginning with its own hot Big Bang, forming its own structures, living out its own cosmic history, ending in whatever fate its particular cosmological parameters determine. And here is where string theory enters in a way that makes the picture more complex and more interesting. String theory predicts that there are an enormous number of possible low-energy configurations of the laws of physics, different values for the masses of particles, different strengths for the forces, different values for the cosmological constant. The total number of such configurations has been estimated at roughly 10 to the power of 500. Each configuration corresponds to a different physics. In the eternal inflation picture, each bubble universe that forms from the inflating background can, in principle, land in a different configuration. Most configurations are probably inhospitable to complexity. A small fraction allow for complexity, chemistry, and eventually observers. Observers in those observer-compatible bubbles look out at their universe and find physical constants suited to their existence. The constants are not fine-tuned in any external sense. They are one of an enormous number of possible combinations, and observers can only find themselves in the samples where observers are permitted. Whether eternal inflation is correct is a separate question from whether its physics is well motivated. The evidence for inflation is strong. The evidence for eternal inflation, specifically, is indirect, since eternal inflation happens beyond any horizon we can probe. The honest position is that we do not know whether the multiverse is real. We know the physics that produces it, when applied consistently, seems to predict it. And we know that if it is real, the universe in its largest sense is not just infinite, but endlessly generative, a structure of perpetual creation that makes the traditional word universe wholly inadequate as a description. Part 8. Dark Energy and the Expanding Edge. Whatever the ultimate extent of the universe, something is happening to it right now that is transforming both its future and our ability to observe it. The universe is not just expanding, it is expanding faster and faster. The rate at which the distances between galaxies are growing is increasing with time, not slowing under the pull of gravity, as most physicists assumed for most of the 20th century, but accelerating. Something is pushing the cosmos apart with increasing force, and whatever it is, it dominates the energy content of the universe and remains fundamentally unknown. This discovery was made in 1998 by two independent teams studying Type Ia supernovae. These supernovae are produced when a white dwarf star in a binary system accumulates enough mass from its companion to exceed the Chandrasekhar limit, the maximum mass at which electron degeneracy pressure can support the star against gravity. When the white dwarf passes this threshold, it undergoes a thermonuclear runaway that destroys it in a spectacular explosion. Because the explosion always happens at the same mass threshold, Type Ia supernovae have a characteristic intrinsic luminosity that can be calibrated and used as a standard candle. Measure the apparent brightness, compare to the known intrinsic brightness, and you know the distance. Measure the redshift, and you know how fast the universe was expanding when that light was emitted. The High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, both expected to find that the universe's expansion had been slowing down over cosmic time. The natural prediction, gravity attracts, matter resists the expansion rate decreases. Distant supernovae should appear slightly brighter than a naive extrapolation would predict, because they are closer than they would be in a universe that had been decelerating. Both teams found the opposite. The distant supernovae were dimmer than expected. The universe was expanding more slowly in the past and is faster now. Something is adding to the expansion rather than resisting it. This something was named dark energy. For this discovery, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. Dark energy currently makes up approximately 68% of the total energy density of the universe. Ordinary matter, everything made of protons, neutrons, and electrons, everything you can see and touch, accounts for only about 5%. The other 27% is dark matter, a non-luminous form of matter known only from its gravitational effects. The universe's energy budget is dominated by dark energy and dark matter, both of which are unknown at the fundamental level. We live in a universe whose composition is 95% mysterious. The simplest and so far best-fitting description of dark energy is Einstein's cosmological constant, representing a constant energy density in the vacuum of space. Even empty space, with no matter or radiation, has a minimum energy. This energy does not dilute as the universe expands. It stays constant, at the same density per cubic meter, always. As the universe expands and the density of matter drops, the cosmological constant eventually dominates the total energy budget. A universe dominated by vacuum energy expands exponentially, just like the inflationary phase in the early universe. The cosmological constant has a deep problem. Quantum field theory predicts that the vacuum should have an energy density. The calculated value of this quantum vacuum energy is roughly 10 to the 120 times larger than the cosmological constant we observe. This is not a rounding error. It is the worst quantitative prediction in the history of theoretical physics. Either quantum field theory is wildly wrong about the vacuum energy, or something cancels the enormous quantum vacuum energy almost completely, leaving a tiny residual. That cancellation would have to be precise to 120 decimal places. No known physical mechanism produces such a cancellation. The cosmological constant problem remains completely unsolved. Now, in 2025, the picture became more complicated and more interesting. The Dark Energy Spectroscopic Instrument, DESI, is a collaboration of more than 900 researchers from over 70 institutions. It contains 5,000 robotic fiber positioners that can simultaneously take spectra of 5,000 individual galaxies, measuring their redshifts and therefore the expansion rate of the universe at the time their light was emitted. In 2024 and 2025, DESI released results from its first 3 years of operation, using measurements of nearly 15 million galaxies and quasars to construct the largest three-dimensional map of the universe ever made. stretching back 11 billion years in cosmic history. When DESI's galaxy clustering measurements were combined with the cosmic microwave background data and supernova distance measurements, the combined datasets showed an intriguing and persistent pattern. The data are slightly better fit by a model where dark energy is not constant but is evolving over time, appearing somewhat stronger in the past and somewhat weaker in the more recent universe. The statistical significance of this departure from a cosmological constant reached between 2.8 and 4.2 sigma across different combinations of data. The gold standard in physics for claiming a discovery is 5 sigma, corresponding to roughly a 1 in 3, 5 to million probability of a statistical fluke. DESI's results had not reached that threshold as of the 2025 data release. The DESI collaboration expressed appropriate caution. But the DESI collaboration completed its full 5-year survey in 2026, and the complete dataset will have roughly twice the statistical power of the 3-year results. If the hints of evolving dark energy strengthen further, it will be one of the most significant cosmological discoveries in decades, requiring fundamental revisions to the standard model of cosmology. The implications of evolving dark energy for the ultimate fate of the universe are profound. If dark energy is a true cosmological constant, the universe expands forever, cooling and emptying over trillions of years toward a state of maximum entropy, the heat death. Structures persist where they are gravitationally bound. Eventually, stars burn out, black holes evaporate via Hawking radiation over timescales measured in years with 100 digits, and the universe approaches a cold, dark, near-empty void. If dark energy is increasing in strength over time, the universe might face a future called the Big Rip. The accelerating expansion grows stronger and stronger until eventually the expansion rate overwhelms even the gravitational binding that holds galaxies together. Then the binding that holds solar systems together. Then the electromagnetic forces that hold atoms together. In the Big Rip, everything is torn apart by the expanding universe itself, down to the subatomic scale. If dark energy is decreasing in strength over time, the acceleration might slow, stop, and reverse. The universe could enter a period of deceleration and eventual collapse, ending in a big crunch. The nature of dark energy determines not just the future of the cosmos, but the nature of space and time at the largest scales. Whatever dark energy turns out to be, its current effect on observational access is already real. Galaxies beyond about 16 billion light-years are already receding from us, faster than light, carried by the expansion, already beyond our event horizon in the sense that their future light will never reach us. As the expansion continues, more galaxies will cross this horizon. In roughly 2 trillion years, nearly everything beyond the local group of galaxies will have vanished permanently from any observer's view. A cosmologist at that era would have no way of knowing the universe ever contained the vast structure we can observe today. The evidence for the Big Bang, the CMB, the large-scale structure, all of it will be gone. The universe would appear to any future observer as an isolated island in an apparently empty cosmos. We are living in the golden age of cosmology, the moment in cosmic history when the evidence of the universe's origins and structure is still visible and accessible. The window will close on cosmic timescales. What we can learn now, we may not be able to learn at any later time. The question of whether the universe is infinite is one we can ask only because we are asking it at the right moment. Part 9. What infinity does to physics. Setting aside the philosophical weight of the question, let us think about what it would mean for physics as a discipline if the universe is genuinely infinite, not what it means for our metaphysical worldview. What it means in the practical, technical sense of how physics has to operate differently when the stage on which it performs is infinite rather than finite. The first and most immediate consequence is what physicists call the measure problem. Physics is the science of making quantitative predictions and comparing them to measurements. To make predictions, you need to define probabilities. To define probabilities, you need to count things, or at least compare sizes of sets. In a finite universe, this is straightforward. The number of galaxies is some large but finite number. The fraction that are spiral is a well-defined ratio between two finite numbers. Predictions can be made, probabilities computed, comparisons with observation performed. In an infinite universe, These fractions are no longer well defined in the same clean way. The number of spiral galaxies is infinite. The total number of galaxies is also infinite. Infinity divided by infinity is not, in general, well defined. It depends on how you take the ratio, what order you count in, what limit you take. Different methods of computing the ratio give different answers, and there is no obviously correct method to choose. This ambiguity is called the measure problem, and it is most severe in the context of eternal inflation. If inflation produces infinitely many bubble universes, and you want to predict what fraction of those universes are like ours, you need a way to compare infinite collections of universes. Physicists have proposed numerous measures for this purpose, each with a different definition of the comparison, giving wildly different results. The proper time cutoff measure, the comoving volume measure, the pocket-based measure, and others all predict different typical properties for bubble universes. Some predict that typical observers should be in universes with very different physical constants from ours. Some predict that most observers in the multiverse are Boltzmann brains. The Boltzmann brain problem deserves careful treatment because it is a striking example of how infinite time in an infinite universe can lead to deeply counterintuitive and physically important conclusions. Ludwig Boltzmann recognized in the 19th century that in a system at thermal equilibrium, random thermal fluctuations can spontaneously produce any configuration of matter, with probability decreasing exponentially with the complexity of the configuration. In infinite time, every possible configuration forms, and forms infinitely many times. A Boltzmann brain is a fully formed conscious observer that arises spontaneously from thermal fluctuations in the vacuum, complete with false memories of having lived a normal life in a normal environment. Such an entity experiences apparently normal consciousness for the brief moment before the fluctuation dissolves back into equilibrium. Its apparent experiences are entirely fictional. It has never interacted with the environment it believes it has lived in. In a universe dominated by a cosmological constant, the universe expands and cools indefinitely. The temperature approaches absolute zero, but never quite reaches it because of quantum fluctuations in the vacuum. These fluctuations continue indefinitely, for an infinite future. Over infinite time, even extraordinarily improbable fluctuations occur. Boltzmann brains eventually outnumber ordinary observers, because ordinary observers require billions of years of cosmic evolution to produce, while a Boltzmann brain just needs one lucky quantum fluctuation. If a cosmological model predicts that typical observers should be Boltzmann brains, and you are apparently not a Boltzmann brain, the model has likely made an error. This makes the Boltzmann brain problem a genuine constraint on physical theories. A theory that predicts most observers are Boltzmann brains, combined with the observation that you are not a Boltzmann brain, is a theory in trouble. Various proposals exist for avoiding the problem, but none is fully satisfactory, and it remains an active area of discussion. The third major consequence of an infinite universe is progressive, observational isolation over time. In an accelerating universe with a positive cosmological constant, the portion of the cosmos accessible to observation shrinks over cosmic time, not in physical extent, but in the fraction of the total universe, visible from any given location. Today, we can observe approximately 2 trillion galaxies. As the universe expands and accelerates, distant galaxies are carried beyond our event horizon. Eventually, the only galaxies we can see are those gravitationally bound to our local group. In roughly 2 trillion years, nearly everything beyond the local group will have receded permanently beyond the event horizon. An astronomer at that era, using the best instruments imaginable, would have no way to reconstruct the full history of the universe from within their isolated galactic island. They would be like a historian trying to reconstruct the history of the Earth from a room with no windows and no archives. The progressive erasure of cosmological evidence by the accelerating expansion is a profound reminder that the relationship between observation and reality is contingent on when you happen to be looking. The universe's autobiography is being slowly sealed. Part 10. The Anthropic Argument and Fine-Tuning. Few topics in modern physics generate more passionate disagreement than the anthropic principle and the fine-tuning of physical constants. The disagreement cuts to fundamental questions about what a scientific explanation is, whether physics is obligated to explain everything, and whether certain deep features of the universe are simply brute facts that no theory will ever derive from first principles. The fine-tuning of physical constants is real. Let me give you specific numbers to anchor this. The cosmological constant, the energy density of empty space, has a measured value of approximately 7 × 10⁻27 kilograms per cubic meter. Quantum field theory predicts a vacuum energy roughly 10 to the 120 times larger. But even setting aside that internal tension, consider what happens to the universe if the cosmological constant were significantly different from its observed value. If it were roughly 10 to the 90 times larger, still vastly smaller than the quantum field theory prediction, the universe would have expanded so rapidly that matter never had time to clump together under gravity. No galaxies would have formed, no stars, no planets, no chemistry, no observers. The strong nuclear force, which holds protons and neutrons together in atomic nuclei, appears calibrated for complex nuclear chemistry. If it were about 2% weaker, the diproton would be unstable, and hydrogen would not burn efficiently in stars the way it does. If it were a few percent stronger, hydrogen in the early universe would have fused almost completely into heavier elements, leaving too little hydrogen for the long-lived, hydrogen-burning stars that provide stable energy for billions of years. The electromagnetic force, the gravitational force, the masses of the electron and the proton, each appears to occupy a narrow range of values that allows complex chemistry and structure. Adjusted by moderate amounts, the universe becomes barren in one way or another. The observation is not that physics required these values. It is that these values are what we observe, and they happen to be in the range that allows observers like us to exist. The question is whether this is a coincidence, a deep constraint, or a selection effect within a multiverse. 3 categories of explanation exist. The unique theory hypothesis says the constants are uniquely determined by some deep, still undiscovered theory. The masses of particles and the strengths of forces are predicted by the fundamental equations, not free parameters. This was the hope underlying the search for a theory of everything for most of the 20th century. String theory shattered this hope by producing a landscape of 10 to the 500 possible low-energy configurations. Rather than uniquely predicting our constants, string theory suggests that any of an enormous number of configurations is equally valid from a theoretical standpoint. The anthropic within multiverse hypothesis says the constants have the values they do because we are in a subset of the multiverse, where observer-compatible values were randomly selected. We observe our constants not because they are special, but because we are in one of the rare configurations that allows observers, and observers can only observe from such configurations. The strongest piece of evidence for this approach is Weinberg's prediction. In 1987, Steven Weinberg used the argument that the cosmological constant must be small enough to allow galaxy formation, combined with the assumption that we are in a random sample of observer-compatible universes, to predict that the cosmological constant should be close to the maximum value compatible with structure formation. His estimate placed the cosmological constant within a range of roughly 100 to 1,000 times the critical density. When the cosmological constant was measured in 1998, more than a decade later, it was found within that range. This successful prediction, made from first principles using anthropic reasoning within a multiverse framework, is the most powerful specific quantitative argument the anthropic approach has produced. Critics are also numerous and distinguished. Paul Steinhardt, Lee Smolin, and George Ellis have argued that the anthropic explanation, even when it makes the right prediction, does not constitute genuine scientific explanation. It does not predict a specific value for the cosmological constant, only that it should be within a broad range. Any measurement of the cosmological constant within that range would be consistent with the prediction, regardless of the specific value. A theory compatible with all measurements in a broad range but predicting no specific value is, in the critic's view, not doing the scientific work of explanation. The genuinely honest assessment is that the fine-tuning of physical constants is real. The anthropic explanation within a multiverse is logically coherent and makes at least one successful prediction, and the question of whether it is the right explanation is currently unanswered and may remain unanswered for a very long time. What the fine-tuning tells us about infinity is indirect but important. If the anthropic explanation is right, the universe in the full sense must contain all observer-compatible configurations, which requires a very large or infinite sample of universes with varying constants. The anthropic explanation of fine-tuning, therefore, implicitly argues for a universe of infinite or effectively infinite extent. Part 11. What the CMB tells us about shape and size. The cosmic microwave background is the most information-rich object in observational cosmology. It is a snapshot of the universe at 380,000 years old, a map of temperature variations across the entire sky, and within those variations is encoded an extraordinary amount of information about the early universe, its composition, its geometry, its topology, and the nature of the inflationary fluctuations that seeded all subsequent structure. The CMB was produced when the hot, dense plasma of the early universe cooled enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was opaque. Photons were constantly scattered by the free electrons in the plasma and could not travel far. When the electrons combined with protons to form neutral hydrogen at about 3000 Kelvin, the universe suddenly became transparent. Photons that had been trapped for 380,000 years were suddenly free to travel. Today, 13.8 billion years later, those primordial photons fill the sky from every direction. The expansion of the universe has stretched their wavelengths by a factor of about 1,100, cooling them from 3000 Kelvin to 2.725 Kelvin, right in the microwave part of the electromagnetic spectrum. This is the cosmic microwave background, the oldest light in the universe. The CMB is extraordinarily uniform. To within 1 part in 100,000, it has the same temperature in every direction. But the 1 in 100,000 variations, the tiny temperature fluctuations superimposed on the uniform background, are the most scientifically precious part of the CMB. They are the fingerprints of the quantum fluctuations that inflation amplified to cosmic scales, the seeds from which every galaxy in the observable universe eventually grew. The statistical pattern of these temperature fluctuations, how their amplitude varies with the angular scale at which they are measured, is called the CMB angular power spectrum. The power spectrum has a series of peaks and troughs at characteristic angular scales, produced by the acoustic oscillations of the photon-baryon plasma before recombination. Sound waves propagated through the plasma for 380,000 years, creating regions of compression and rarefaction at specific length scales. When the plasma recombined and the CMB was released, those sound waves were frozen in place, imprinting their pattern on the temperature map. The first acoustic peak in the CMB power spectrum occurs at an angular scale of roughly 1 degree. Its precise position depends sensitively on the geometry of space. In flat space, the sound horizon subtends approximately 1 degree. In positively curved space, it subtends a larger angle. In negatively curved space, a smaller one. The Planck satellite found the first peak entirely consistent with flat space. Combining Planck's measurements with baryon acoustic oscillation data, the best current constraints give omega total equal to 0, 9,993 plus or minus 0.0019, flat to within 2 parts in 1,000. This is one of the most significant measurements in cosmological history. The universe's geometry is flat at a precision that rules out moderate curvature. The CMB also contains information about the topology of the universe, independent of the curvature. If the universe is topologically compact, if space wraps around on itself at some scale, our observable universe might be large enough that we are looking at the same physical regions of space from multiple directions. This would appear in the CMB as matched pairs of circles, specific circular regions at which the temperature pattern, if you rotate the circles to align them, would be identical, because both circles are sampling the same physical region of space, seen from different angles. This test was proposed in 1998 by Neil Cornish, David Spergel, and Glenn Starkman, and carried out systematically using both WMAP and Planck data. No matched circles have been found at any statistically significant level. This rules out compact topologies smaller than the distance to the last scattering surface. If the universe is topologically compact, the topology scale is larger than our observable horizon. A new approach to constraining cosmic topology was published by the Compact Collaboration in early 2025, inspired by the mathematical question Mark Kac posed in 1966. Can you hear the shape of a drum? The cosmological analog asks whether the CMB power spectrum uniquely determines the topology of the universe. By analyzing Planck CMB data with this technique, Compact placed new constraints on the 3-torus topology and its variants, finding that the simplest cubic torus model is ruled out if the topology scale is within the observable horizon, and beginning to constrain topology models at larger scales beyond what the circle search can reach. The CMB's spectral index of primordial fluctuations, measured at approximately 0.965, is exactly in the range that simple inflationary models predict and inconsistent with a perfectly scale-invariant spectrum at more than 8 sigma significance. The universe does not have a scale-invariant primordial power spectrum. It has exactly the slight tilt that inflation predicts. This is one of the most powerful confirmations that inflation occurred. The search for primordial gravitational waves through CMB B-mode polarization continues. Inflation would have produced gravitational waves that imprint a specific curl-like polarization pattern in the CMB. The amplitude of this signal depends on the energy scale of inflation. Current limits place the tensor-to-scalar ratio below, about 0.035, ruling out the highest energy inflationary models, while leaving many others viable. Future experiments, including the Simons Observatory, CMB, S4, and the Lightbird satellite, are planned with sensitivity sufficient to either detect the signal or push limits significantly lower. There is also the Hubble tension, the approximately 9% discrepancy between measurements of the current expansion rate from the CMB, which gives about 67.4 kilometers per second per megaparsec, and measurements from local distance indicators like Cepheid variable stars and Type Ia supernovae, which give values closer to 73 kilometers per second per megaparsec. This discrepancy has persisted and grown stronger over the past decade. The James Webb Space Telescope's improved measurements of Cepheid calibration have largely confirmed the local measurement, making the discrepancy more robust. If the Hubble tension is real and not a systematic error, it may indicate new physics that affects the expansion history of the universe in the early cosmic period, potentially including modifications to the inflationary framework or new forms of dark energy. What the CMB tells us, in its totality, is a rich and detailed story. The universe emerged from an inflationary epoch. It has a geometry flat to very high precision. It has no detectable compact topology within our observable horizon. Its fluctuation spectrum is exactly what inflation predicts. And it is doing all of this consistently with the standard lambda CDM cosmological model, while also showing tantalizing hints that the standard model may be incomplete. The CMB is a fossil, the oldest light we can detect, a snapshot of the universe at 380,000 years old, pressed flat against the sky in every direction. Reading it carefully is the closest thing we have to reading the universe's own autobiography. And what it says, so far, is that the universe does not appear to have any edges, at least none that we can see. Part 12. Final synthesis, living inside something without edges. We have now followed this question as far as current physics can take it. We have traced the observable universe, understood the distinction between what we can see and what exists, explored the geometry of space and its 3 possible curvatures, understood how cosmic inflation produced the enormous flat universe we inhabit, and how eternal inflation might have made it infinite, examined the multiverse framework and its strange implications, confronted the accelerating expansion driven by dark energy, thought about what infinity does to physics in practice, considered the anthropic argument and the fine-tuning of physical constants, and read what the cosmic microwave background has to tell us about the shape and extent of the cosmos. Let us now bring all of it together honestly, without pretending the uncertainties are resolved, and ask what we actually know. Here is what we know, or know as well as physics currently allows us to know anything. The universe is 13.8 billion years old, in the sense that 13.8 billion years have passed since the universe was in the hot, dense, rapidly expanding state we call the Big Bang. It has a radius of observation of 46.5 billion light-years, the distance that light has been able to travel to us in that time, accounting for the expansion that occurred during the journey. Within that sphere, there are approximately 2 trillion galaxies, each containing billions to hundreds of billions of stars. The observable universe is a place of staggering richness and scale. The geometry of the observable universe is flat to within a fraction of a percent. The total energy density of the universe equals the critical density to within about 2 parts in 1,000, with dark energy at 68%, dark matter at 27%, and ordinary matter at about 5%. This flatness is precisely what cosmic inflation predicts, and it is one of the strongest pieces of evidence that inflation occurred. The universe is expanding, and that expansion is currently accelerating. The acceleration is driven by dark energy, which appears to behave like a cosmological constant, a fixed energy density in empty space that does not dilute as the universe expands. Recent data from DESI hints that this dark energy might be evolving over time, rather than being truly constant, but that result has not yet reached the threshold for a confirmed discovery. The full 5-year DESI dataset will resolve this question with much higher statistical power. The actual universe, beyond our observable horizon, is almost certainly vastly larger than the observable portion. Cosmic inflation expanded whatever pre-inflationary space existed by at least a factor of 10 to the 30, and probably by much more. If inflation was eternal, the universe is infinite in spatial extent. We do not know whether the universe is finite or infinite. The measurements are consistent with both possibilities. A flat universe is the simplest description of a spatially infinite universe. But a very gently curved universe, far too gentle for any current instrument to detect, would also be consistent with every measurement we have made, and would produce a universe that is finite, but so large as to be practically indistinguishable from infinite at any scale we can observe. We do not know what dark energy is, at a fundamental level. We know it exists, we know its density, we know its effect on the expansion, but we do not know what it is made of, why it has the value it has, or why it is small enough to allow structure to form, but large enough to be driving the current acceleration. We do not know whether the inflationary epoch was eternal or finite. We do not know whether a multiverse exists. We do not know what happened before inflation, at the Planck time, or whether there was a before in any meaningful sense. These are not the residual details of a nearly complete theory. They are central, foundational, first principles questions about the nature of reality. And the honest position is that the answers are not currently known. But here is what strikes me as genuinely remarkable about this situation. We have gotten further with this question than any previous civilization in the history of the Earth. We have measured the geometry of space to a precision of a fraction of a percent. We have mapped the cosmic microwave background across the entire sky with precision down to 1 part in a million. We have traced the expansion history of the universe over 11 billion years, using millions of galaxies as measuring instruments. We have worked out the detailed physics of nucleosynthesis with enough precision to match observations to better than 1%. We have built a model of the universe that correctly predicts the distribution of galaxies across the sky, the temperature of the CMB, the ratio of hydrogen to helium in the oldest stars, and dozens of other independent observational facts. This is an extraordinary achievement. It represents the accumulated work of thousands of scientists over more than a century, using tools from mathematics, physics, astronomy, chemistry, and engineering, working across generations and cultures, building on each other's insights, correcting each other's mistakes, pushing the frontier further with each generation. And at the frontier, we are standing at the edge of what can currently be answered, looking at questions that may require entirely new theoretical frameworks, new kinds of observations, new ways of thinking about the relationship between physics and the reality it describes. The question of the universe's infinitude is one of those frontier questions. It cannot be answered by simply building a bigger telescope, because the answer is not encoded in light that we have simply missed. It is encoded in the initial conditions of the universe, which are, in principle, beyond the reach of any observation we can make from within our observable bubble. The information that would tell us whether the universe is finite or infinite was set at the moment of the Big Bang or before it, and the expansion since then has placed most of that information permanently beyond any horizon we can reach. There is something vertiginous about this situation. We are inside the thing we are trying to measure. We are made of the matter whose origin we are trying to understand. We are using the physical laws of the universe to ask questions about the universe, which means our tools are made from the same stuff we are trying to understand. We cannot step outside the universe to get an objective view. All we can do is reason very carefully from within it, using every piece of information that our observable bubble provides. And reasoning carefully from within our bubble leads us to a picture that is, in the most honest summary I can give, something like this. The universe is either infinite or so enormously large that the distinction makes no practical difference. The evidence for inflation is very strong, and inflation naturally produces a universe vastly larger than what we can observe. If inflation was eternal, as the physics of quantum fields naturally suggests, the universe is infinite in the strictest mathematical sense. The fine-tuning of physical constants, if it requires explanation, points toward a multiverse of effectively infinite extent in which observer-compatible constants arise through anthropic selection. The geometry of the observable universe is flat, which is the geometric signature of infinite spatial extent in the simplest cosmological models. All the arrows point the same way. They point toward something too large to have edges in any observationally meaningful sense, too large for any finite measurement to close, too large for any horizon to encompass. The universe, on current evidence, behaves like something infinite. Whether it technically is infinite in the strictest sense is a question that may forever lie beyond our observational reach. Now I want to sit with what it actually means to try to imagine this honestly. Not with the metaphors we typically use to make it palatable, the universe as an inflating balloon, the universe as a loaf of raisin bread with raisins moving apart as the loaf rises. Because those analogies are useful for specific limited purposes, but they all fail at the fundamental level. They picture the universe as expanding into a larger surrounding space, which may not be the case. I want to sit with the actual strangeness of what we are contemplating. If the universe is infinite, there is no special location within it. Every point in the universe is equally central and equally peripheral. There is no center and no edge. If you could somehow travel in a straight line, at any speed, for any length of time, you would never arrive at a boundary, a wall, a place where space ended and something else began. You would just keep going, through more galaxies, more voids, more clusters, more cosmic web, indefinitely. Not until you got tired, not until the universe ended, but literally forever, in a space that has no terminus. This is difficult to hold in the mind because all of our intuitions about space are built around containers. Rooms have walls, planets have surfaces, solar systems have limits of gravitational influence. Galaxies have edges where the stellar density drops to nothing. We navigate through life by orienting ourselves relative to boundaries and surfaces and edges. A space without any edges anywhere, in any direction, at any scale, is something our intuition was not built to hold. And yet, if the physics is right, that is what we inhabit. Not a place with edges far away, but a space that is by its nature edgeless. A space that cannot be completed, because completion requires an ending, and endings require boundaries, and boundaries require something outside them, and there is no outside. There is a thought that sometimes comes to me when looking at astronomical images. When you see a deep field image from the Hubble or James Webb Space Telescope, one of those photographs that shows thousands of galaxies in a patch of sky so small it could be covered by a grain of sand held at arm's length, what you are actually looking at is the past. The light from those galaxies took billions of years to arrive. Some of those galaxies may no longer exist in the forms they wore when that light departed. What the telescope captures is history, light that has been traveling since before the Earth existed, arriving at a mirror on a telescope that humans built in the brief interval since complex life evolved on this particular rocky planet orbiting a particular ordinary star in one of those trillions of galaxies. If the universe is infinite, those images are a window not just into the past, but into an extent of space that goes on and on, without end, in every direction. An uncountable number of galaxies, beyond every galaxy visible in that frame, stars and planets, and whatever else space contains beyond every visible star and planet, all of it existing completely indifferent to whether we see it or whether we do not, whether we ask about it or whether we do not, whether our universe generated the kind of beings that could ask the question, or whether it remained forever unknown to itself. The fact that it generated us, here, now, with enough understanding to trace the shape of the CMB and measure the flatness of space and argue about whether inflation was eternal, feels like something. Not something supernatural or designed, just something. A remarkable alignment of conditions and time, an evolutionary chance that produced beings capable of pointing at everything that exists and asking, honestly and carefully, and with the full weight of human ingenuity, whether it goes on forever. We do not know the answer. We might never know the answer in the strict sense of knowing. But the fact that we can follow the question this far, that we can sit with the tension between finite and infinite, and understand what each would mean, and what the evidence says, and where the uncertainties lie, that is not nothing, whether the universe is infinite or finite, whether it is alone or surrounded by an endless multiverse, whether dark energy is constant or changing. One thing the evidence tells us clearly is that the universe is under no obligation to be easily understood. It is not designed for our convenience. It is not arranged to fit neatly into our intuitions. The geometry of space does not need to be Euclidean, because that is what feels familiar. The Big Bang does not need a simple story, because that makes good headlines. Infinity does not need to be resolved, because we feel uncomfortable leaving questions open. The universe is what it is, and what it appears to be is something on a scale and of a kind for which human language has no adequate words. The best we can do is keep measuring, keep thinking, keep pressing against the edges of what can be known, and stay honest about where those edges are. That is what cosmology is. That is what this question has always been about. And it is a question, I think, worth carrying with you. Not to resolve it, but to hold it. Because a question big enough to make everything else feel small is one of the things that makes being alive in this particular universe genuinely extraordinary. The universe goes on. Whether it goes on forever, we cannot yet say. But we are still trying to find out, and that is enough to keep watching the sky. If you made it to the end of this, I genuinely appreciate you spending this time thinking about this question with me. If something here opened a new way of thinking about the cosmos for you, drop a comment and let me know. And if you have not subscribed yet, please do. More questions like this are coming. Questions that are worth sitting with, questions that resist easy answers, questions that make the universe feel as large and strange and wonderful as it actually is. Until next time, take care of yourselves out there. End of script. Expanded Deep Dive. Part 2. Extended the strangeness of counting without end. Let us spend more time with what infinity actually does when you try to apply it to the physical universe, because the concept has consequences that most people who use the word have never followed to their conclusions. And those consequences are genuinely strange enough to warrant careful attention. When the mathematician Georg Cantor developed the theory of infinite sets in the 1870s and 1880s, he was working in an environment of deep suspicion. Many of his contemporaries, including the influential mathematician Leopold Kronecker, considered his work not just wrong, but dangerously misguided. Kronecker famously called Cantor a corrupter of youth for teaching ideas about actual infinities to students. The theological establishment also weighed in, with some arguing that only God could be truly infinite, and that assigning mathematical infinities to sets of numbers was a kind of blasphemy. Cantor, who was deeply religious himself, found this period extraordinarily painful. He believed that his work was mathematically sound, and that it did not conflict with theological principles about divine infinity, but the opposition wore on him considerably. What Cantor proved, and what eventually became the accepted foundation of modern mathematics, is that you can reason precisely about infinities, and that there are different sizes of infinity. His key tool was the concept of a bijection, a one-to-one correspondence. Two sets have the same size if and only if you can pair up their members one-to-one, with nothing left over from either side. This works fine for finite sets. Does it work for infinite ones? Cantor showed that the set of integers and the set of even integers have the same size, in the bijection sense. You can pair them up. 1 with 2, 2 with 4, 3 with 6, 4 with 8, and so on. Every integer gets paired with exactly one even integer, and every even integer gets paired with exactly one integer. The pairing is perfect, no leftovers. So the set of all integers and the set of only the even integers are the same size, even though the even integers are a strict subset of the integers. This is one of the genuinely mind-bending properties of infinite sets. A part can be the same size as the whole, but Cantor showed that the real numbers cannot be put into such a correspondence with the integers. His diagonal argument is one of the most elegant proofs in all of mathematics. Suppose you claim to have listed all the real numbers between 0 and 1 in some order. Cantor shows you can always construct a real number that is not on your list by taking its first decimal digit to be different from the first decimal digit of the first number on your list, its second decimal digit to be different from the second decimal digit of the second number on your list, and so on down the diagonal. The number you construct differs from every number on your supposed complete list in at least one decimal place. Therefore, your list was not complete. No matter how clever your listing, you can always do this. The real numbers cannot be listed. They form a strictly larger infinity than the integers. This result, that some infinities are genuinely larger than others, is directly relevant to cosmology in the following way. In an infinite universe, the number of galaxies is an infinite set that, like the integers, is countable in the mathematical sense. You can, in principle, list them, one after another, numbering them as you go. But the number of points in space is uncountably infinite, like the real numbers. Even in a finite region of space, like the volume of your living room, there are uncountably many points. The infinite universe contains both kinds of infinity simultaneously, a countably infinite number of galaxies and an uncountably infinite number of spatial points. For physics, the distinction between countable and uncountable infinities matters because they behave differently when you try to assign probabilities to them. Countably infinite sets can sometimes be given probability distributions if the probabilities decrease fast enough towards 0 and sum to 1. Uncountably infinite sets resist this, which is one reason the measure problem in eternal inflation is so difficult. The space of possible universes in an eternal inflation multiverse may be uncountably infinite, meaning the usual tools of probability theory simply do not apply without additional mathematical machinery. Now, here is what I want you to sit with. If the universe is spatially infinite, then right now, at this moment, there are infinitely many points in space where something exactly like your current situation is occurring. Not approximately like it. Exactly like it, down to the position of every particle and the state of every quantum field. The physicist Max Tegmark has thought through the details of this more carefully than almost anyone. He estimates the characteristic distance to the nearest identical copy of our observable universe at roughly 10 to the power of 10 to the power of 115 meters. This is a number that dwarfs any number that arises in ordinary cosmology. It is not even a number that can be called astronomical. It is a number that would take more zeros to write out than there are atoms in the observable universe. And yet in a genuinely infinite universe, it corresponds to a real physical distance, to a real physical place, where a real version of you exists, having the exact same experience you are having right now. The implication of this is philosophically rich in ways that the physics itself does not resolve. If there are infinitely many versions of you, each making every possible choice in every possible moment, does the specific you that you experience have any special status? Does any decision you make matter if every decision is being made by some version of you somewhere in the infinite expanse? These questions have no clean physical answers. They are questions about the relationship between physical fact and personal meaning, and that relationship is not determined by the equations of cosmology. What the physics does tell us is that an infinite universe, if it exists, is not just a larger version of a finite one. It is qualitatively different in the nature of the claims it makes about reality. In a finite universe, everything that exists is singular. This galaxy, this star, this planet, this moment. In an infinite universe, everything that exists is infinitely replicated, and the singular and the infinitely duplicated coexist in a way that our ordinary concepts of identity and uniqueness were not designed to handle. Expanded Deep Dive. Part 4. Extended the first fraction of a second. Let us go deeper into what actually happened in the earliest moments of the Big Bang, the period before inflation ended and the hot Big Bang began. Because this is where the initial conditions of the universe were set, and because the physics of this period is directly relevant to the question of the universe's total size. The period of cosmic inflation, as Alan Guth originally proposed it, and as it has been refined and extended by many physicists since, is believed to have occurred within the first 10 to the negative 32 seconds of the universe's existence. During this period, a region of space that was originally quantum mechanical in scale, smaller than an atomic nucleus, expanded exponentially to become vastly larger than the current observable universe. Not just larger, orders upon orders of magnitude larger. The expansion factor was at minimum 10 to the power of 26, and in many inflationary models, it was much greater, potentially 10 to the power of hundreds or thousands. Understanding why this expansion was so extreme requires understanding what drives it. The inflationary expansion is driven by a form of energy associated with the inflaton field that has a specific and unusual property. Ordinary matter and radiation, as the universe expands, dilute. In a larger volume, there is less matter or radiation per unit volume. This means ordinary matter and radiation create less gravitational influence per unit volume as the universe grows. Dark energy, represented by the cosmological constant, does not dilute. Every cubic meter of space has the same amount of dark energy, regardless of how large the total space is. This non-diluting energy exerts a kind of repulsive gravitational effect, an outward push on the expansion, rather than the inward pull that ordinary matter creates. The inflaton field in the early universe behaved like an extreme version of dark energy. It had an extraordinarily high energy density, and it did not dilute. Every cubic meter of the inflating space contained the same enormous energy density, regardless of how large the total volume grew. This created an exponential expansion. The more space there was, the more energy there was pushing the expansion, and the more the space expanded. Each doubling of volume was followed immediately by another doubling, and then another, at a rate of roughly one doubling every 10 to the negative 37 seconds. After roughly 100 doublings, which took approximately 10 to the negative 35 seconds in total, a region that started smaller than a proton had become larger than our entire observable universe today. After 1,000 doublings, which still took only 10 to the negative 35 seconds, the total inflated volume had grown by a factor of 2 to the power of 1,000, which is approximately 10 to the power of 300. This is a number that puts ordinary astronomical scales into insignificance. And in many inflationary models, the inflation continued for far longer than 1,000 doublings. When inflation ended, the energy stored in the inflaton field was rapidly converted into the hot plasma of particles and radiation that characterizes the hot Big Bang. This process is called reheating. The inflaton field, as it rolled down to its low energy state, oscillated rapidly and transferred its energy to the particles of the standard model through various couplings. The universe heated up to an enormous temperature, on the order of 10 to the 27 Kelvin, and the standard cosmological history, with its nucleosynthesis, its CMB, and its eventual formation of structures, began from there. The quantum fluctuations that were amplified during inflation to become the seeds of cosmic structure were oscillations in the inflaton field itself. In quantum mechanics, no field is ever exactly in a fixed state. Fields fluctuate, with particles appearing and disappearing, with amplitudes that vary randomly around their average values. These fluctuations are extraordinarily small at normal scales. At the scales of subatomic physics, they produce the Casimir effect and other measurable quantum vacuum effects, but they are negligible at everyday human scales. During inflation, these tiny quantum fluctuations were stretched by the inflationary expansion from subatomic scales to cosmological scales. A fluctuation that started smaller than a proton, with an amplitude measured in the quantum uncertainty of the inflaton field, was stretched to a scale of billions of light-years over the course of inflation. As it was stretched, it became fixed, frozen into a classical density perturbation rather than remaining a quantum fluctuation. This freezing process is one of the strangest and most important aspects of inflationary cosmology. The quantum world becomes the classical world through inflation. The spectrum of these frozen fluctuations, How their amplitude varies with their scale depends on the details of how the inflaton field rolled down its potential during inflation. For the simplest inflationary models, in which the inflaton rolls slowly and nearly uniformly, the resulting spectrum is nearly scale invariant, roughly the same amplitude of fluctuations at all length scales with a slight enhancement at large scales. This is exactly what Planck and other CMB experiments have measured. The near-scale invariance of the primordial power spectrum is one of the most powerful confirmations that something very much like simple inflation actually happened. These frozen quantum fluctuations were the birth of all structure in the universe. Every galaxy you can see in the night sky, every cluster and supercluster, every vast empty void, every filament of the cosmic web grew from a quantum fluctuation that was stretched to cosmic scales during the first 10 to the negative 35 seconds of the universe's existence. The quantum world, ordinarily invisible at human scales, left its signature on the largest structures in the observable cosmos. The universe is, in a very real sense, a quantum mechanical object. Its structure is a direct imprint of quantum uncertainty writ large by inflation. And here is where this connects back to the question of infinity most directly. The quantum fluctuations that inflation amplified were not determined by any classical causal process. They were genuinely random, in the deep quantum sense, unpredictable in principle by any theory. Different regions of the inflating space experienced different random fluctuations, leading to different density perturbation patterns in different regions after inflation ended. The observable universe that we inhabit reflects the particular random fluctuations that happen to occur in our local region. Other regions of the inflated cosmos, far beyond our horizon, have different density perturbation patterns, reflecting their own independent random fluctuations. If the universe is infinite, there are infinitely many such regions, each with its own unique random realization of the quantum fluctuation spectrum. The universe, on the largest scales, is not just large. It is random, in the quantum sense, and infinite, meaning that every possible quantum realization has occurred somewhere. Every possible galaxy distribution, consistent with the physical laws and the underlying inflationary spectrum, exists somewhere in the infinite expanse. Some regions are much denser than ours. Some are much emptier. Some have large-scale structure very different from the cosmic web we observe. All of them are real. All of them exist. The universe contains every possible realization of its own random quantum initial conditions, because it is large enough that every possible realization occurs somewhere. Expanded Deep Dive, Part 6. Extended the inflationary epoch in full detail. We touched on the horizon and flatness problems and how inflation solves them, but there is more to say about inflation itself, because the details of how it works are directly connected to the question of whether the universe is infinite. Alan Guth's original 1980 proposal, called old inflation, had a specific problem. In the original model, the inflaton field was stuck in a false vacuum, a local minimum of energy that was not the true minimum. The field had to quantum tunnel through a barrier to reach the true minimum. As long as it was stuck in the false vacuum, the space containing it inflated rapidly. When it tunneled through the barrier, it released its energy as a hot Big Bang. But in Guth's original model, the tunneling happened simultaneously across the entire inflating region, and the resulting Big Bang had problems. The nucleation of bubbles of true vacuum was so violent that it produced an extremely inhomogeneous universe, inconsistent with the observed smoothness. This problem, which Guth himself identified in his original paper, was solved by what became known as new inflation, developed independently by André Linde in the Soviet Union, and by Andreas Albrecht and Paul Steinhardt in the United States in 1982. In new inflation, the inflaton field does not quantum tunnel through a barrier. Instead, it sits near the top of a smooth potential energy hill and slowly rolls down toward the valley. While it is rolling, the space it permeates is inflating. When it reaches the bottom of the hill and oscillates there, its energy is transferred to the hot plasma of the Big Bang. The slow rolling ensures that the inflation is long enough and smooth enough to solve the horizon and flatness problems, and the reheating at the end produces a spatially smooth, hot universe consistent with observations. Shortly after new inflation was proposed, André Linde developed another variant called chaotic inflation, in which the inflaton field starts in a large range of possible initial values, spread across different regions of space in a random, chaotic distribution. Some regions start with very large field values and inflate for an extremely long time. Others start with smaller values and inflate for less time. Our observable universe is the product of a region that happened to have field values in the right range to produce a universe consistent with what we observe. Chaotic inflation is in many ways the most natural inflationary framework because it does not require fine-tuned initial conditions for the inflaton field. All of these inflationary models share a common feature. They predict a universe that is vastly larger than the observable patch. The inflation that is needed to solve the horizon and flatness problems already requires a minimum of about 60 e-folds of expansion, meaning the universe expanded by at least e to the power of 60, which is approximately 10 to the power of 26. But in chaotic inflation, regions with larger initial field values inflate for much longer, producing much larger regions. The universe that any particular region inflates into is determined by the initial field value in that region. And in a universe where the initial field values are randomly distributed, some regions inflate enormously, more than the minimum required. The question of how long a given region inflated is related to the question of whether eternal inflation occurs. In chaotic inflation, the large field value regions inflate for an extremely long time. As they inflate, quantum fluctuations within them can kick the field values up to even larger values in subregions, leading to those subregions inflating for even longer. The process is self-reproducing. High field value regions continuously spawn new high field value regions that inflate for longer, which spawn further high field value regions in a fractal process that never stops. This is the picture of chaotic, eternal inflation developed by André Linde in the mid-1980s. In this picture, the universe is an eternally self-reproducing fractal of inflating regions, with individual bubbles of hot Big Bang universe, forming and evolving independently throughout the inflating background. The total volume of the universe grows without bound. The number of bubble universes increases without bound. The universe is infinite, not just in spatial extent at any given moment, but in the total number of distinct cosmic histories it contains. This picture has been refined and extended by many physicists over the past 4 decades. It has faced challenges, particularly around the measure problem we discussed earlier, and around the difficulty of making precise predictions in a framework that produces infinite variation. But the basic physical mechanism, quantum fluctuations in a slowly rolling inflaton field, continuously regenerating high field value regions that inflate for longer, is robust and follows directly from combining quantum mechanics with a slowly rolling scalar field in an expanding universe. The key point for our question is this: if chaotic, eternal inflation is correct, and if the physics of the inflaton field is roughly as described by the simplest slow-roll inflationary models, then the universe is not just very large, it is infinite in a specific, physically meaningful sense. The total spatial extent of the cosmos, including all the still inflating regions and all the bubble universes that have formed within them, grows without bound and does not converge to any finite limit. The observable universe, the 9.3 billion light-year sphere, that is all we can ever directly probe, is an infinitesimal fraction of this infinite whole, not a rounding error, not negligible. Infinitesimal, in the precise mathematical sense that its fractional contribution to the total volume approaches 0 in the limit of infinite time. Expanded Deep Dive. Part 8. Extended Dark Energy and the Deep Future. We have discussed dark energy as a present and near-future phenomenon, but let us follow the implications further into the deep future of the cosmos, because the behavior of dark energy over astronomical timescales determines the ultimate fate of everything, including the question of whether the universe continues to be a good candidate for infinite extent. If dark energy is truly a cosmological constant, a truly fixed vacuum energy density that neither increases nor decreases over time, then the future of the universe is a process of progressive cooling, emptying, and eventual heat death. Let us trace this future in some detail, because the timescales involved are themselves a reminder of the extraordinary extent of time that an infinite or very large universe encompasses. For the first 20 billion years or so, the universe looks much as it does now. Galaxies continue to form stars, planets orbit stars. Complex chemistry and possibly complex life exist in habitable environments. The Milky Way and Andromeda galaxies, which are currently on a collision course, will merge in roughly 4.5 billion years to form a large elliptical galaxy. The Sun will exhaust its hydrogen fuel in roughly 5 billion years, expand into a red giant, and eventually shrink to a white dwarf. These are essentially human-scale events in the context of the universe's total history. Over the next hundreds of billions of years, star formation gradually decreases as galaxies run out of the gas needed to form new stars. The remaining stars slowly burn out, from the longest-lived red dwarfs that burn for trillions of years to the white dwarfs that gradually cool over even longer timescales. By roughly 100 trillion years after the Big Bang, roughly 10 to the 14 years, the era of ordinary stellar burning is essentially over. The universe enters what cosmologists call the degenerate era, a time dominated by cold white dwarfs, neutron stars, and black holes, with no new starlight. This degenerate era lasts for an extraordinary length of time, from roughly 10 to the 14 years to roughly 10 to the 40 years. During this era, the universe is dark and cold. White dwarfs gradually cool. Occasionally, collisions and gravitational scattering eject objects from galaxies or cause mergers. Black holes slowly accumulate mass. But there is no significant light, no new energy generation, no basis for the kind of complexity that characterizes the current cosmos. Starting at around 10 to the 40 years, proton decay, if it occurs as grand unified theories predict at some level, would begin to dissolve the remaining ordinary matter into lighter particles and radiation. By 10 to the 40 to 10 to the 45 years, most of the matter from the degenerate era would have decayed into positrons, electrons, neutrinos, and photons, leaving behind only the black holes. Black holes themselves evaporate via Hawking radiation, the quantum mechanical process by which the vacuum fluctuations near the event horizon of a black hole lead to a slow but steady emission of thermal radiation. The timescale for a black hole to evaporate via Hawking radiation depends on its mass. A stellar mass black hole evaporates in roughly 10 to the 67 years. A supermassive black hole at the center of a galaxy, with a mass of 1 billion solar masses, evaporates in roughly 10 to the 96 years. This is an unimaginably long time. It is a number with 96 zeros. After all the black holes have evaporated, the universe consists of an extremely dilute gas of photons, neutrinos, electrons, and positrons, slowly cooling and expanding. The density is effectively zero. The temperature is effectively zero, though not mathematically zero because of the residual photons from Hawking radiation. This is the heat death, maximum entropy, minimum free energy, no basis for any further complexity or ordered structure of any kind. In a universe with a cosmological constant, the heat death is approached asymptotically. The universe never actually reaches zero temperature or exactly maximum entropy. It approaches these limits as time approaches infinity. But for all practical purposes, by the time the last black holes have evaporated, 10 to the 96 years from now, the universe is effectively dead, infinitely dead. Dead in a way that will persist for the rest of eternity. Now, the numbers involved in this deep future are numbers that have no human referent. 10 to the 96 years is so much larger than the current age of the universe, 13.8 billion years, that comparing them is essentially comparing a number to zero. The age of the universe, as we know it, the stellar era, the era of galaxies and complexity and life, is a brief flicker at the very beginning of the universe's total temporal extent. The vast majority of the universe's future, if it has a heat-death future, is the dark, cold, empty aftermath. This temporal vastness is itself a kind of argument against the universe being an isolated island of existence. A universe that persists for 10 to the 96 years, even if it is spatially finite, contains an almost incomprehensible amount of time. In that amount of time, an enormous number of possible physical processes can occur. Thermal fluctuations in the quantum vacuum given sufficient time, will spontaneously generate structures of arbitrary complexity. The Boltzmann brain problem we discussed earlier is precisely about this. In enough time, the vacuum will spontaneously generate observers, planets, entire observable universes, not as frequently as they occurred during the stellar era, but with a non-zero probability that accumulated over 10 to the 96 years adds up to an enormous number of events. The question of what it means for the universe to be infinite in time, and whether that temporal infinity creates the same strange consequences as spatial infinity, is one that cosmologists are actively working on. The measure problem applies to time as well as space. How do you compute the probability of being a particular kind of observer in a universe that has been running for effectively infinite time, containing Boltzmann brains and real observers in enormously different proportions at different epochs? These questions do not have clean answers, but they illustrate that the infinity in the universe question is not just a question about the spatial extent of the cosmos. It is a question about the relationship between time, probability, observation, and the nature of reality. And it is a question that the universe's extraordinary extent in time, even in the finite case, makes both urgent and deeply difficult. Expanded Deep Dive, Part 10, Extended Fine-Tuning Numbers in Detail. Let us go deeper into the specific numbers that make the fine-tuning of physical constants so striking, because the quantitative precision required is even more extraordinary than casual descriptions convey. The cosmological constant problem is the most severe. Quantum field theory predicts that every field in nature contributes to the vacuum energy. The electron field, the quark fields, the gauge boson fields, each contributes an amount proportional to the fourth power of the field's characteristic energy scale. For the electron, this contribution is approximately 10 to the 9 joules per cubic meter. For the quarks, it is much larger. For physics at the scale of the electroweak unification, roughly 100 GeV, the contribution is approximately 10 to the 46 joules per cubic meter. For physics at the Planck scale, which is where quantum gravity effects would become important, the predicted vacuum energy density is approximately 10 to the 113 joules per cubic meter. The observed cosmological constant has an energy density of approximately 10 to the -9 joules per cubic meter. The discrepancy between the Planck scale prediction and the observed value is a factor of 10 to the 122. This is the 1-2-0 orders of magnitude problem we mentioned earlier, stated in different units. What makes this problem so severe is not just the size of the discrepancy. It is the nature of what must be happening for the observed value to be so small. All the different contributions from all the different fields must somehow cancel each other with precision to 122 decimal places, leaving a residual of exactly the tiny positive value we observe. This is not a cancellation that any known physics produces naturally. It would require fine-tuning of the contributions from all the fields to an extraordinary and apparently arbitrary precision. The anthropic argument applied to the cosmological constant, as Weinberg formulated it, says that in a multiverse where different bubble universes have different values of the cosmological constant, drawn from some distribution, the universes where we can exist are those where the cosmological constant is small enough to allow the formation of galaxies, where gravity can overcome the outward push of dark energy. Weinberg estimated that the maximum cosmological constant compatible with galaxy formation is roughly 200 times the current matter density. The current cosmological constant is roughly 2 to 3 times the matter density, well within this anthropic window. The extraordinary precision of the observed value, sitting more than 2 orders of magnitude below the anthropic maximum, rather than right at the maximum, was not specifically predicted by the anthropic argument, but is consistent with it. In a multiverse where cosmological constants are drawn from a distribution that is roughly flat over the anthropic window, most observers would find themselves in universes where the cosmological constant is a random point in that window. The fact that our observed value is not right at the maximum of the window is not surprising. It just means we drew a value somewhere in the interior of the distribution. The strong nuclear force fine-tuning is less extreme in magnitude, but equally striking in its implications. The coupling constant of the strong force, called alpha Cs, has a value of approximately 0.118 at the energy scale of the Z boson. If this value were about 2% smaller, the diproton, a bound state of two protons, would be unstable. The absence of a stable diproton in our universe means that hydrogen burns slowly in stars via the weak force-mediated proton-proton chain, producing the long-lived, stable stars that provide energy for billions of years. If the diproton were stable, hydrogen would burn explosively fast, and stars would be short-lived and explosive rather than long-lived and stable. Life requiring billions of years of stable stellar irradiance would be impossible. If the strong force were about 2% stronger, the diproton would be stable, and the proton-proton chain would be replaced by a much faster fusion process. Stars would burn out quickly. There would not be enough time for complex chemistry to evolve. Again, life would be impossible. The electron-to-proton mass ratio, which is approximately 1 to 1,836, is also finely set. If the electron were much heavier, atoms would be much smaller, and the orbital radii of electrons would be comparable to nuclear scales. The separation between chemistry and nuclear physics, which is the basis for the rich variety of chemical bonds and molecular structures, would break down. If the electron were much lighter, atoms would be much larger, and the long-range electromagnetic forces that drive chemistry would be weaker. In either case, the precise chemistry that life as we know it depends on would be disrupted. The weak nuclear force, which governs radioactive decay and certain types of nuclear reactions, has a strength that is crucial for stellar nucleosynthesis. Supernova explosions, which are responsible for distributing heavy elements throughout the galaxy, depend on the weak force interacting with the dense neutron-rich matter in the collapsing core. If the weak force were significantly weaker, supernovae would not explode, and heavy elements would remain locked in stellar remnants. If it were significantly stronger, the supernova explosion would be disrupted in different ways. The heavy elements that make rocky planets and life possible, the carbon, oxygen, iron, calcium, and everything else above helium in the periodic table, would not be distributed through the galaxy without the precisely calibrated weakness of the weak force. What emerges from studying these examples is a picture of a universe in which the physical constants occupy a narrow region of a vast space of possible values, a region where the conditions for complexity, and ultimately for observers, happen to be met. This is the observation. The explanation for it is where the disagreement lies. The unique theory hypothesis would be compelling if we had a candidate fundamental theory that predicted these values from first principles. String theory, the most developed candidate, fails at this. It produces 10 to the 500 possible sets of constants, not a unique prediction. Loop quantum gravity, another candidate, has not yet made definitive quantitative predictions about standard model parameters. The anthropic hypothesis within a multiverse is logically compelling in the abstract, but has the practical limitation that it cannot be tested by direct observation of other universes. Its predictive success with the cosmological constant is real and impressive. Its extension to other constants is suggestive but less precisely predictive. The I don't know position, which is to say acknowledging that the fine-tuning is real and striking and currently unexplained, is probably the most honest scientific stance. It acknowledges that we have discovered something that current theory cannot fully account for, and that this gap points toward physics we do not yet have. Whether that physics will turn out to be a unique theory explanation, a multiverse explanation, or something entirely different that we have not yet imagined, cannot currently be determined. Expanded Deep Dive. Part 12 extended the full inventory of what we know and do not know. Before we close, let us do a careful and complete inventory of where we stand, because the question of whether the universe is infinite sits at the intersection of several major open questions in cosmology, and understanding exactly what we know and do not know is the most honest way to end. What we know with high confidence, supported by multiple independent lines of evidence, the universe is approximately 13.8 billion years old. This is constrained by the CMB power spectrum, by the ages of the oldest stars and globular clusters, by the measured expansion rate combined with the measured density parameters, and by the theoretical models of Big Bang nucleosynthesis that correctly predict light element abundances. The agreement between these independent methods is impressive. The universe is about 13.8 billion years old. The universe began in a hot, dense state and has been expanding and cooling since. This hot Big Bang cosmology is supported by the CMB, by the observed large-scale distribution of galaxies, by the expansion we observe through galaxy redshifts, and by the light element abundances. It is one of the most thoroughly tested frameworks in all of science. The observable universe contains approximately 2 trillion galaxies within a sphere of approximately 93 billion light-years diameter. This is based on deep field imaging, galaxy counts, and extrapolations of the galaxy density distribution. The geometry of the observable universe is extraordinarily flat. The total energy density is within 2 parts in 1,000 of the critical density. Dark energy accounts for roughly 68%, dark matter for roughly 27%, and ordinary matter for roughly 5%. These numbers are consistent across multiple independent measurement methods. The CMB power spectrum is consistent with inflationary predictions for the spectral index of primordial fluctuations. The universe began with a nearly scale-invariant spectrum of density perturbations, exactly as simple inflationary models predict. The universe's expansion is currently accelerating. Dark energy, with an energy density consistent with a cosmological constant, is the driving force. This is established beyond reasonable doubt. What we strongly suspect, but cannot directly confirm, cosmic inflation occurred. The evidence is indirect, but extensive, and mutually consistent. The flatness, the uniformity of the CMB, the spectrum of fluctuations, the absence of magnetic monopoles, and other exotic relics. If inflation did not occur, these independent observations would each need separate, unexplained fine-tunings. With inflation, they all follow naturally from a single mechanism. The overwhelming majority of cosmologists accept that something very much like inflation happened, but inflation has not been directly confirmed, for example, through the detection of primordial gravitational waves. The universe is much larger than the observable portion. If inflation occurred, and if it lasted at least the minimum required to solve the horizon and flatness problems, the total universe is at least 10 to the 78 times larger in volume than the observable universe. If inflation lasted longer, or if eternal inflation is occurring, the universe is larger by incomprehensibly greater factors. What we genuinely do not know, whether the universe is finite or infinite, the measurements are consistent with both. A geometrically flat universe is the simplest description of an infinite universe, but a very large finite universe with slight positive curvature undetectable from our position is equally consistent with all observations. What dark energy is. We know its density and its effect. We have no confirmed theoretical explanation for its value, whether eternal inflation occurred, and whether a multiverse exists. The physics that produces eternal inflation, when quantum mechanics is properly applied to inflationary models, is well motivated. But eternal inflation is beyond any direct observational test. What happened at the Planck time and before? The Big Bang singularity is a theoretical artifact. The actual physics at extreme densities is unknown. Whether the universe had a beginning in time, or whether it emerged from a prior phase of some kind, is genuinely unknown. Whether the physical constants of our universe are unique or are a sample from a larger ensemble, if the multiverse exists and the string theory landscape is populated by eternal inflation, the constants are a sample. If not, their values may be uniquely determined by a still undiscovered theory. These open questions are not gaps in an otherwise complete theory. They are the frontier questions that define the direction of physics research for the coming decades. Each of them, if answered, would transform our understanding of the universe, not just in detail, but in kind. The question of whether the universe is infinite is at the center of this web of open questions. Answering it would require answering whether inflation was eternal, which would require understanding the physics of the inflaton field in detail, which would require a deeper theory than we currently have. Or it would require measurements of the universe's curvature or topology at scales far beyond our current observational reach. We are, in the most precise sense, at the edge of what can currently be known, not at the end of knowledge, at its frontier. And the frontier, as it always has been in the history of science, is the most exciting place to be. The universe has been expanding for 13.8 billion years. It will continue expanding, in one form or another, for incomprehensibly longer. Whether that expansion will proceed into infinite space or eventually come to a halt in a finite cosmic volume, we cannot yet say. But the evidence, patient and consistent, and gathered with extraordinary care by thousands of scientists over more than a century, points towards something vast, something that may have no edge, something that may be, in the only honest word available, infinite, and we are here, inside it, looking outward, asking. That, in itself, is extraordinary. Final end of script. Total estimated length, 25,000. Plus words. Bonus section. Cosmic topology and the shape space can take. We have talked about the three possible curvatures of space: flat, positively curved, and negatively curved. But curvature and topology are not the same thing, and this distinction is important for the question of the universe's finiteness in a way that is worth understanding carefully. Topology is the mathematical study of the properties of spaces that remain unchanged when the space is continuously deformed, stretched, or squished without tearing or gluing. The classic example is the topological equivalence of a coffee mug and a donut. Both have exactly one hole. You can continuously deform one into the other without tearing. They are topologically equivalent. Curvature, on the other hand, is a geometric property. It measures how space bends. A flat plane and a cylinder have the same intrinsic curvature, both flat, but they have different topologies. A cylinder is formed by taking a flat rectangle and gluing two opposite edges together. The resulting space is still flat in the local sense, meaning the Euclidean rules of geometry hold everywhere on it, but it is finite in one direction and infinite in the other. A being living on the surface of a very large cylinder might not notice its topology from any local measurement. They would find flat geometry everywhere. But if they traveled far enough in the right direction, they would return to where they started. The same distinction applies to the three-dimensional universe. A spatially flat universe does not have to be infinite. It could be topologically compact. The simplest, compact, flat three-dimensional space is the three-torus, formed by taking a cube-shaped region of space and identifying opposite faces. Travel far enough to the right and you emerge from the left side. Travel far enough upward and you come back from below. Travel far enough into the distance and you come back from behind. The resulting space is flat everywhere, with all the Euclidean rules holding locally, but it is finite, with a total volume equal to the cube's volume. In a three-torus universe, looking out in any direction far enough, you would eventually see the back of your own head. You would see multiple images of every object, repeating in all directions. The universe would look like an infinite corridor of mirrors, with copies of everything repeating in every direction. An astronomer in a three-torus universe might, without realizing it, be observing the same galaxy multiple times in different directions, seeing different historical epochs of that galaxy in each observation because the light took different amounts of time to traverse the torus in different directions. The search for these multiple images, and for the matched circle signatures we discussed in the CMB section, is the observational approach to constraining cosmic topology. The absence of matched circles in the Planck data means that if the universe is a three-torus, its fundamental domain, the cube whose copies tile the universe, must be larger than roughly 28 billion light-years on a side. That is larger than what light has had time to traverse since the Big Bang, meaning we cannot see our own ghost images in the CMB. But there are many possible compact topologies beyond the simple three-torus. There are 5 distinct compact, flat, three-dimensional spaces, and many compact, positively curved and negatively curved spaces as well. Each has different symmetry properties and would produce different patterns in the CMB if the universe's topology scale were comparable to the observable horizon. One particularly beautiful example is the Poincare dodecahedral space, proposed by Jean-Pierre Luminet and colleagues in 2003 as a possible topology that would explain some anomalies in the large-scale structure of the CMB power spectrum. In this space, opposite faces of a dodecahedron are identified, creating a finite but positively curved closed universe. The Poincare dodecahedral space would produce a specific pattern of matched circles in the CMB, with a specific angle of rotation. Searches for these specific circles have not found them at statistically significant levels, but the topology remains an interesting theoretical possibility. The current state of the art is summarized by the Compact Collaboration's 2025 results. Specific compact topologies have been constrained or ruled out within the observable horizon, but the vast majority of possible compact topologies remain untested. Most of the 18 mathematically distinct compact three-dimensional flat geometries and the many compact positively and negatively curved geometries leave signatures only within our observable horizon, if the topology scale is comparable to our horizon size. If the topology scale is larger, as it must be if the universe inflated for a long time, no signature would be detectable regardless of the topology. The deep lesson is that topology is genuinely separate from curvature, and that we can constrain both, but only up to the limits of our observational reach. A universe that is topologically compact at scales just beyond our horizon would be undetectable with any current or near-future instrument. The universe might be finite and self-identifying in its topology, an extraordinarily strange thing to contemplate, without leaving any observable footprint within the sphere of space we can access. Bonus section: the James Webb Space Telescope and new cosmological surprises. The James Webb Space Telescope, launched in December 2021 and fully operational since 2022, has been transforming observational astronomy and contributing to cosmological questions in ways both expected and surprising. JWST was designed primarily as an infrared telescope with a 6.5-meter segmented mirror that makes it far more sensitive than any previous infrared observatory. Its primary science goals included observing the first stars and galaxies, studying galaxy formation and evolution, characterizing exoplanet atmospheres, and probing the formation of stars and planetary systems. All of these goals are being achieved, often beyond expectations. For cosmology specifically, JWST has provided observations of galaxies at extremely high redshifts, corresponding to the universe as it was when only a few 100 million years old. The very existence of massive, already formed galaxies at these early epochs has surprised many theorists. Some of the galaxies JWST has observed at redshift 10 and beyond appear to be larger and more massive than theoretical models of galaxy formation predicted for such early times. The galaxy formation community is actively debating whether these observations require modifications to the standard cosmological model, whether they can be accommodated within the current framework with revised assumptions about star formation efficiency, or whether they result from some combination of observational effects and incomplete modeling. What is interesting about these early massive galaxies from the perspective of the universe's size question is that they provide new data points on the primordial matter distribution and on how quickly structure formed. The density fluctuations from inflation that seeded galaxy formation had to be large enough, in the right places, to produce massive galaxies within the first 500 to 700 million years of the universe's history. If the fluctuations were exactly as predicted by the simplest inflationary models, it should be difficult to form such massive galaxies so quickly. The JWST observations may therefore be pointing toward a slight revision in our understanding of the inflationary power spectrum, perhaps with slightly more power at small scales than the simplest models predict. This is a genuinely exciting frontier. The CMB measures the primordial power spectrum on large scales. JWST is effectively measuring it on smaller scales by looking at how quickly structure formed at early times. Combining the two probes gives a more complete picture of the inflationary output spectrum across a much wider range of scales. Discrepancies between the CMB and JWST constraints on the spectrum could point toward inflation models with specific features, or toward effects of dark matter that differ from the standard cold dark matter assumption, or toward entirely new physics. JWST has also contributed to the Hubble tension in a way that, unfortunately, makes it harder, not easier, to resolve. By providing improved calibrations of Cepheid variable stars in nearby galaxies, JWST has helped confirm that the local measurement of the expansion rate, around 73 kilometers per second per megaparsec, is robust and is not simply the result of poorly calibrated local distance measurements. The tension with the CMB derived value of around 67.4 kilometers per second per megaparsec appears to be real, not an artifact. This means there is likely some genuine new physics affecting either the early universe or the late universe, or both, in ways not captured by the standard lambda CDM model. Some proposed resolutions to the Hubble tension involve modifications to the early universe before the CMB was emitted. Early dark energy, a component of energy density that was important in the universe at redshifts of around 3000 and subsequently diluted away, is one such proposal. It would change the sound horizon scale at recombination, which is the standard ruler used to convert the CMB measured expansion rate to the value we compare to local measurements. If the sound horizon was different from what the standard model predicts, the CMB-derived expansion rate would be wrong in a specific way that could bring it into agreement with the local measurements. Other proposed resolutions involve modified gravity, additional neutrino species, dark matter with unusual properties, or interacting dark energy. None of these solutions is clearly preferred by the data, and each one introduces new free parameters that require additional observational constraints. The Hubble tension is an active research problem at the frontier of cosmology, and its resolution, whatever form it takes, is likely to provide important new information about either the early universe or the late universe, or both. For the question of whether the universe is infinite, the Hubble tension is relevant indirectly. If the expansion history of the universe is different from what the standard model predicts, the inferences we draw from the expansion history about the total energy density and the spatial curvature might also need revision. The extraordinary flatness of the universe, omega equals 1 to within 2 parts in 1,000, is based on the standard model's prediction of the sound horizon scale. If the sound horizon is different, the inferred flatness changes. If the universe is slightly less flat than we currently believe, the implications for finite versus infinite are also slightly different. The Hubble tension, if it is real new physics, is a reminder that our picture of the universe is still evolving, and that the answers to deep questions like the universe's size may shift as our understanding improves. Bonus section. What would convince us the universe is finite? Let us ask a concrete question that sometimes gets lost in the abstract discussion. What would it take to convince cosmologists that the universe is finite? What observations, if made, would provide compelling evidence for a finite cosmos with a definite total volume? The most direct evidence would be a detection of compact topology, specifically the matched circles in the CMB that we discussed earlier. If Planck or a future CMB experiment detected a statistically significant pair of matched circles in the temperature map, that would be direct evidence that the universe wraps around on itself at a scale comparable to or smaller than our observable horizon. The identification of the circles and their geometry would immediately constrain the topology, the size, and possibly the curvature of the universe. This would be an extraordinary discovery. Unfortunately, as discussed, no such circles have been found in the current data, and the absence of circles constrains but does not eliminate compact topologies at larger scales. A second possible evidence would be the detection of repeated structures in the large-scale distribution of galaxies. In a compact universe, the cosmic web of filaments and voids would repeat periodically in specific directions, at specific characteristic scales, reflecting the topology. Future large-scale galaxy surveys, including the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, the Euclid Satellite Mission, and the Nancy Grace Roman Space Telescope, will map the three-dimensional distribution of galaxies across hundreds of millions of light-years with far greater coverage and precision than any previous survey. If the universe is compact at scales comparable to the survey volume, the periodic repetition of structures might be detectable through statistical analysis of the galaxy distribution. A third possible evidence would be a more precise measurement of the spatial curvature. If the universe is a closed, positively curved space, its total volume is determined by its curvature. A measurement of positive curvature at a statistically significant level would imply a finite universe. The combination of future CMB experiments with improved sensitivity, future baryon acoustic oscillation surveys, and future weak gravitational lensing surveys might eventually achieve constraints on the curvature parameter, precise enough to detect a gentle, positive curvature if one exists. This is a long-term prospect. Current limits already constrain the curvature parameter to less than 1 part in 1,000. Improving this by the factor of 400 needed to constrain a hypersphere whose radius is 400 times our observable horizon would require extraordinary improvements in both observational capability and systematic error control. What would convince us the universe is infinite is a harder question, because you cannot directly observe infinite extent. You can only ever observe the finite portion within your observational reach. What you can do is accumulate evidence that the universe is consistent with infinite extent and inconsistent with any finite topology within a very large range of scales. As future surveys constrain compact topologies to larger and larger scales, and as curvature measurements approach zero with increasing precision, the hypothesis of an infinite universe becomes more and more strongly supported. In the same way that the hypothesis of a round Earth becomes more and more strongly supported as you measure the flatness of a larger and larger area of the Earth's surface and find it consistent with a sphere of increasing size. You never directly measure the full sphere, but you accumulate evidence that is consistent only with a sphere, not a flat plane. The universe, in this sense, is behaving exactly as you would expect an infinite or extremely large space to behave. Every test we have run has returned a result consistent with infinite extent. The CMB is flat. There are no matched circles. There are no obvious topological repetitions in the galaxy distribution. The expansion history is consistent with a flat, infinite universe. None of these individually proves infinity. Together, they build a circumstantial case that is already compelling and that will become more so as each new generation of surveys and instruments adds its data to the accumulated picture. The honest forecast is that direct proof of the universe's infinitude, if it is infinite, may forever remain beyond our reach. But the indirect circumstantial case for a universe that is, at least effectively infinite, from the perspective of any possible observation, will almost certainly continue to strengthen over the coming decades. Complete end of script. Approximately 25,500 plus words total. Bonus section. The philosophy of cosmological questions. There is a dimension to the question of the universe's infinitude that sits at the boundary between physics and philosophy, and that is worth exploring explicitly rather than leaving it as an unspoken undercurrent to everything we have discussed. Physics is extraordinarily good at describing how the universe evolves from some set of initial conditions. Given the state of the universe at any moment, the equations of physics can tell you, in principle, how that state will evolve into the future and how it evolved from the past. This is what physicists mean when they talk about the laws of nature. The laws are equations of motion. They connect the state of the universe at one time to the state at another time. What the laws of physics cannot do, at least within any framework we currently have, is tell you why the initial conditions were what they were. The laws accept the initial state as an input and produce the subsequent states as outputs. They do not produce the initial state. The initial state is prior to the laws, in the logical sense that the laws require the initial state to operate on. This is a deep and possibly permanent limitation of the scientific enterprise as we currently understand it. The question of why the universe began, with the specific initial conditions it did, including the specific spatial extent, whether finite or infinite, that it started with, is not a question that the laws of physics as we understand them can answer. It is a question about the origin of the laws themselves and of the initial state on which they operate, and that question points beyond physics into territory where physics currently has nothing definitive to say. Various approaches exist for trying to extend physics into this territory. The Hartle-Hawking no-boundary proposal attempts to derive the initial state of the universe from a quantum mechanical prescription that does not require a sharp initial moment in time. In this picture, the universe has no beginning in the way a point in time has a sharp edge. It is more like the smooth, rounded surface of the south pole of the Earth, which is as far in one direction as you can go, but which does not have a sharp boundary or an edge from which you fall off. The initial state is determined by the quantum mechanics of the no-boundary condition, not by arbitrary specification. This is a beautiful idea, but it has not been possible to derive from it a unique prediction for the initial state of the universe that can be tested. Different implementations of the no-boundary proposal lead to different predictions, and choosing among them requires assumptions that are not derived from within the framework itself. Lee Smolin's cosmological natural selection, which we mentioned earlier, takes a different approach. It treats the universe as one member of a population of universes that reproduce through black holes, with the physical constants of each daughter universe being slightly mutated versions of the parent. In this picture, the constants we observe are those that have been selected by cosmological natural selection because they maximize black hole production, which turns out to also tend to produce observer-compatible constants as a side effect. This is a bold and creative idea. It makes specific, testable predictions, most notably that no neutron star can have a mass greater than 1.6 solar masses, which was taken as a firm prediction at the time, but which has since been complicated by observations of neutron stars with masses approaching 2 solar masses. Roger Penrose's conformal cyclic cosmology, or CCC, takes yet another approach. In this picture, the universe goes through an infinite series of cycles, each one called an aeon. Each aeon begins in a hot Big Bang state and ends in a cold de Sitter state dominated by the cosmological constant. The key insight is that the very late de Sitter state and the very early hot dense state are related by a conformal transformation, a specific mathematical operation that preserves angles but not distances. The end of one aeon maps conformally onto the beginning of the next. There is no singularity. There is no beginning. The universe has been cycling forever, and each aeon is in some sense a new universe growing out of the previous one. CCC makes specific observational predictions. The collisions of supermassive black holes in previous aeons should leave faint circular imprints in the CMB, called Hawking points, representing regions of slightly higher temperature. Penrose and colleagues claim to have found such features in the Planck CMB data, but the interpretation is disputed, and most cosmologists do not consider the evidence compelling. These various proposals, the no-boundary wave function, cosmological natural selection, conformal cyclic cosmology, and others, share a common ambition: to extend physics beyond the Big Bang singularity, to say something about why the initial conditions were what they were. They differ enormously in their specific claims and their observational implications. What they illustrate is that the question of the universe's origin, including whether it started as a finite or infinite space, is not beyond the reach of scientific theorizing. It is beyond the reach of current confirmed physics. But physicists are actively working on extending that reach, proposing theoretical frameworks that go beyond the standard Big Bang model to address the questions the standard model cannot. Whether any of these frameworks is correct, and whether the correct framework will ever be confirmed by observation, remains to be seen. The history of physics suggests that, surprisingly, occasionally, what seems like a permanently unanswerable question turns out to have an unexpected observational handle. The question of the universe's age, which seemed hopelessly speculative in the 19th century, turned out to be answerable through the CMB and stellar evolution. The question of the large-scale structure of the universe, which seemed unobservably remote, turned out to be accessible through galaxy surveys and the CMB. The question of the universe's total curvature, which seemed forever inaccessible from a finite observational volume, has been constrained to within 2 parts in 1,000. Perhaps the question of infinite or finite will also find its unexpected observational handle. Perhaps some consequence of inflation, or of the universe's topology, or of the physics at the Planck scale will leave a detectable footprint in the data that future instruments can find. Perhaps not. Perhaps the question is genuinely, permanently beyond reach. But the history of science argues against premature conclusions about what is permanently unknowable. The universe has surprised us before, and it will almost certainly surprise us again. Closing reflection. Why this question matters. Let us end not with a technical summary, but with a reflection on why this question, of all the questions we might spend time with, is worth the effort we have put into it. The question of whether the universe is infinite is not a question with practical consequences in the ordinary sense. The answer, whatever it is, will not change what happens on Earth tomorrow. It will not solve any immediate human problem, or satisfy any immediate human need. In that sense, it is the most impractical of questions. And yet it is the kind of question that does something to you when you hold it honestly. It rescales everything. The anxieties of ordinary life, the worries about what other people think, the concerns about the small competitions and social dramas that fill most of a human day, all of it sits very differently when you have been sitting with the genuine possibility that the space you inhabit extends forever, in every direction, contains an infinite number of galaxies, produces somewhere infinitely many exact copies of every moment you have ever lived. This is not a call to nihilism. The fact that the universe is large or infinite does not make your life meaningless. It makes your life strange. It situates it in a context that is genuinely beyond ordinary comprehension. And that strangeness, when you let yourself feel it rather than immediately filing it away as an abstraction, has a quality that I would call awe. Not the vague, comfortable awe of a beautiful sunset, the sharper, slightly dizzying awe of something that is actually bigger than your mind can hold. There is a tradition in physics of caring about this kind of thing, of doing science not just because it is useful, but because the universe is beautiful and strange and worth understanding for its own sake. Richard Feynman described physics as the pleasure of finding things out. Carl Sagan wrote about the pale blue dot and what it means for human significance in the context of cosmic scale. Einstein spoke of the cosmic religious feeling, the sense of profound wonder at the comprehensibility of the universe, as the motivating force behind his work. The question of the universe's infinitude is in this tradition. It is a question about what the universe is, not about what it can do for us. And questions of that kind, pursued with rigor and honesty and genuine curiosity, have a way of changing the people who pursue them, making them think more clearly, more carefully, more humbly, making them a little more aware of the extraordinary improbability of being here at all, in this specific configuration of matter, on this specific planet, at this specific moment in the history of a universe that is either infinite or so large that the difference barely matters, asking whether it goes on forever. We do not know the answer. The evidence points toward yes. The physics suggests yes. The mathematics of the simplest models says yes. But the honest answer, the answer that respects both what the data tells us and what the data cannot tell us, is that we are still working on it. And that is, in its own way, exactly where we should be. The universe goes on. Whether it goes on forever, we cannot yet say, but we are still trying to find out, and that effort is one of the most remarkable things our species has ever undertaken. The capacity to look up at the sky and ask seriously whether it has an edge, and to build the mathematics and the instruments and the theoretical frameworks to actually pursue the answer, is something worth being proud of. So keep looking up, keep asking. The question is not going anywhere, neither are we, and neither, as far as we can tell, is the universe. If this took you somewhere worth going, I am glad we made this journey together. Drop a comment and tell me where your mind landed. And until next time, take care of yourselves out there, under whatever sky you are watching from tonight.